Hello there, and welcome to Science for Sleep, where curiosity gets cozy and science takes the long, quiet road through the stars. Tonight, our journey drifts toward a corner of the universe so distant, so powerful, and so silent that it almost feels like a dream whispered in the dark. We're going to explore something enormous, invisible, and utterly fascinating. A black hole so vast that it dwarfs imagination itself. Its name is TON 618, and it is the most powerful black hole we've ever found. Before we begin to unravel what that really means, I'd love to know, where in the world are you listening from tonight? Maybe you're lying in bed, the room dim and still, your thoughts moving slowly after a long day. Maybe you're on a late train, watching the night slip by through the window, stars fading behind the city lights. Whatever moment you're in, you and I are now sharing this one tiny thread of time together, connected by curiosity, following a sound that reaches across the dark. If you find this quiet exploration comforting or interesting, or if it simply helps your thoughts slow down, I'd be very grateful if you gave this little corner of calm a like, maybe a subscribe, or shared it with someone else who could use a gentle dose of wonder. It helps this peaceful space reach those who might need it too. So, let's take a breath. The world outside can wait. For now, we're going to drift beyond the edges of what's visible and trace the faint light of something that should be impossible to see. Because in the quiet gulf between galaxies, there is a point of gravity so strong that not even light can escape. Yet somehow, paradoxically, it glows brighter than entire galaxies combined. The story of TON 618 begins not with an explosion or a star's birth, but with the faintest whisper of light travelling for more than 10 billion years to reach our telescopes. Imagine that. The photons from this object began their journey when the universe was young, when galaxies were still forming, when our own sun wouldn't exist for another 5 billion years. Everything that has ever happened on Earth. The formation of oceans, the rise of mountains, the first living cells, the slow march of evolution, all of it has unfolded while that light was still crossing the emptiness to arrive here. When you look at TON 618, you aren't just looking far away, you're looking deeply back in time. A black hole, in essence, is the simplest thing imaginable and the most extreme. It's what happens when gravity wins completely. When enough mass collapses into a small enough space, the pull of gravity becomes so strong that nothing, not even light, can climb back out. What's left is a region of space defined by absence, an event horizon marking the point of no return. Inside that boundary, the laws of physics as we know them stop working in any familiar way. It's not that the rules break, it's that the rules themselves no longer make sense there. But TON 618 is not a small black hole. Not the kind that forms from the collapse of a single star. It's a supermassive black hole, millions or even billions of times more massive than our Sun. In TON 618's case, we estimate a mass around 66 billion suns. To give that a sense of scale, if you place TON 618 at the centre of our solar system, its event horizon would stretch well past the orbit of Neptune. It's not a dot in space. It's a region vast enough to swallow planetary systems whole, a gravity well so deep that space itself bends steeply into it like fabric stretched to tearing. The number, 66 billion solar masses, is almost impossible to visualize. Our minds aren't built for that kind of magnitude. We can imagine a mountain, a planet, maybe even a star, but billions of stars worth of mass condensed into one singular object that defies every ordinary frame of reference. And yet it's real, or at least as real as anything can be in astronomy, where our evidence is often made of light gathered through mirrors and mathematics. TON 618 reveals itself not through darkness but through brilliance. Around its unseen centre swirls an accretion disk, a flat, luminous whirlpool of gas and dust spiralling inward, heating to extraordinary temperatures as friction and gravity tear it apart. That disk emits more light than entire galaxies, shining with the energy released by matter falling toward oblivion. So while the black hole itself cannot be seen, The violence of its feeding makes it one of the brightest known objects in the cosmos. That light, faint but measurable, was first noticed not as a mystery, but as a data point. In the 1950s and 60s, astronomers cataloguing radio sources found a peculiar entry labelled TON 618. At first, it was simply another object in a survey of the sky, its name derived from the Tonantzintla Observatory in Mexico where it was recorded. Only later, with improved instruments, did scientists realise they were looking at a quasar, one of those distant, energetic beacons powered by supermassive black holes devouring matter at their cores. To call it bright is an understatement. If TON 618 were somehow placed 50 million light-years away, still unimaginably distant, it would shine in our night sky almost as bright as the full moon. Of course, it's not that close. It's about 10.4 billion light-years away, meaning its light has been stretched, or redshifted, by the expansion of the universe. What we see now is an ancient signal, a snapshot of what the universe looked like when it was less than a third of its current age. And yet, for something so remote, it affects us in subtle ways. Every observation of TON 618 challenges our understanding of how such massive black holes form. The universe at that early time shouldn't have had enough years under its belt to grow something so large through normal processes. If black holes form from collapsing stars and grow by slowly consuming surrounding matter, there simply wasn't enough time between the Big Bang and the era when TON 618 already existed as a cosmic giant. So the question lingers, how did it become so enormous, so quickly? The search for answers pulls us into deeper territory. Maybe black holes can merge faster than we expect, combining their masses like drops of water in a rainstorm. Maybe, in the early universe, conditions allowed for direct collapse black holes. Immense clouds of gas that skipped the star stage entirely and fell straight into black holes millions of times the sun's mass. Or maybe there's something we still don't understand about the physics of accretion and growth in extreme environments. Whatever the explanation, TON 618 is a living puzzle piece from the dawn of cosmic history. It's interesting how something that far away, something utterly beyond reach, can make us question the fundamentals of our own reality. The light from TON 618 doesn't just illuminate a distant region of space, it casts a reflection on how little we truly know about our cosmic neighbourhood. When we measure its spectrum, we see fingerprints of hydrogen and helium stretched into deep red wavelengths by the universe's expansion. Those lines tell us not only how far away TON 618 is, but also how fast the universe has been expanding since that ancient time. Each photon carries a record of distance, motion, and change encoded in colour. Even though we can't see the black hole directly, we can sense its influence in the way it shapes everything around it. Gas clouds drawn into its gravity whirl at nearly the speed of light. Magnetic fields twist into jets that shoot out from the poles, spearing through intergalactic space for thousands of light years. These jets are among the most powerful structures in existence, narrow beams of plasma accelerated by forces we barely grasp, bright enough to be seen across the universe. The scale of it borders on incomprehensible, yet it follows the same physical principles that govern a whirlpool in your bathtub. The difference is only in size and consequence. There's a quiet irony in all of this. We call black holes black, but the ones we discover are usually among the brightest things we can observe. They shine not because of what they are, but because of what they do, the way they transform falling matter into energy, light, and radiation. They are paradoxes made visible. TON 618, for all its terrifying mass, exists as a glowing point in our telescopes, a candle in the cosmic fog, proof that even the deepest gravity can produce light. When astronomers study objects like this, they're not just gathering facts. They're reaching backward in time, collecting the story of how the universe built itself. Every distant quasar is a fossil of energy, a record of chaos that helps sculpt the galaxies we see today. The Milky Way, calm and spiral, owes its form to similar forces once raging in its youth. Perhaps our own central black hole, Sagittarius A, was once as voracious as TON 618, shining across the cosmos before settling into its quiet middle age. In that sense, TON 618 might not be just a curiosity. It could be a glimpse of our own galaxy's distant past, a reminder of how violent and creative the universe once was. Thinking about such distances can stretch the mind until it almost hurts. Light travelling 10 billion years means 10 billion years of uninterrupted motion at the ultimate cosmic speed limit. No rest, no pause, no obstacle. Each photon left its home before our planet formed and arrived here, striking the mirror of a telescope, only to be converted into a tiny electric signal and stored on a computer chip. Somewhere in that chain, human eyes looked at the data and saw meaning, a pattern, a measurement, a realization that this faint point represented something bigger than any human scale. There's a kind of quiet reverence in that act of observation, a small intelligence noticing the echo of something immense. If you think about it, the very fact that we can detect TON 618 at all is extraordinary. The universe is mostly empty, expanding and dim. The energy that reaches us from such distances is unimaginably weak. And yet, with the right instruments, we can read that light and reconstruct entire histories. We can tell how fast matter was moving, how hot it was, how much energy it released, and even what elements were present. All from light so faint that you'd never see it with your eyes. That's the miracle of astronomy, finding meaning in whispers. For now, TON 618 remains the record holder, the largest black hole confidently measured. There may be others larger still, hidden deeper in the cosmos or shrouded by dust and distance, but none have yet revealed themselves. It's humbling to remember that we've mapped only a small portion of the observable universe. The night sky above you may look calm, but beyond it are billions of galaxies, each with a black hole at its heart, each one quietly shaping the fate of everything around it. TON 618 just happens to be the one so powerful that its light reached us across nearly the entire span of cosmic time. When you close your eyes and picture it, don't imagine a hole or a void. Picture instead a great storm of light swirling around a silent centre, a whirlpool of fire suspended in nothing. The centre itself is invisible, perfectly black, but everything near it glows with desperate energy as it falls inward. Matter that once drifted peacefully through intergalactic space now circles the drain of gravity, heating until it emits X-rays and ultraviolet light that would tear atoms apart. From that chaos, beauty emerges, not in peace, but in the sheer harmony of physics working at its limit. In a way, TON 618 is a symbol of extremes. It represents what happens when nature pushes every equation to its boundary, when matter, energy and space-time meet at their breaking point. And yet, despite its violence, it exists quietly now in the depths of the cosmos, far removed from anything we can touch. The distance makes it safe, almost gentle, an object of study rather than fear. We can admire it, analyse it, and let its existence remind us of how vast the universe truly is. The light from TON 618 is still travelling, still expanding outward, still telling its story to anyone capable of listening. Somewhere billions of years from now, that same light may reach another world, another species with its own telescopes and questions. Maybe they'll look back and see what we saw, a bright point in the dark, proof that something immense once burned at the edge of creation. And so, as you rest here, listening to the slow drift of these thoughts, you're sharing a moment connected to that light. The universe is old, enormous, and indifferent, but in the midst of all that distance, human awareness acts like a mirror, catching a fraction of it and turning it into understanding. That act, noticing, wondering, caring to know, is what links us to the stars. TON 618 may be beyond reach, but the curiosity it inspires is close, immediate, alive in the mind that imagines it. In the quiet of this moment, it's enough to let the image settle. A distant point of brightness from a time before Earth existed, powered by a black hole so massive that its gravity bends the fabric of reality. Its light is older than the oceans, older than every living thing that's ever looked up at the night sky. And still, it arrives, steady, patient, carrying its message across eons. That message is simple, that even in the deepest darkness, something endures, something shines, and that we, small and temporary, can still listen. When you think of darkness, you probably imagine something empty. A quiet room after the lights are out. The void between stars. The unseen space behind your eyelids as you drift towards sleep. Darkness in our daily lives is absence. The lack of light. The pause before morning. But in the universe, darkness can be a source. It can shine, not by giving off light itself, but by shaping it, bending it, and fueling it in ways that defy intuition. Black holes are the purest example of that paradox, and among them, TON 618 stands as the ultimate contradiction, a place of complete darkness surrounded by the brightest light ever recorded from so far away. Light and darkness in space don't behave like they do on Earth. Here, shadows exist because something blocks light. In the universe, darkness often means energy. A black hole doesn't glow, but the material around it does, ferociously. Matter spirals inward, compressed by gravity and friction, until atoms are stripped of electrons, turning the surrounding disk into a cauldron of plasma millions of degrees hot. From that maelstrom comes radiation across every wavelength. Visible light, ultraviolet, X-rays. It's a place so bright that telescopes can see it from billions of light years away, even when the source itself is hidden behind an event horizon from which no light escapes. That's why TON 618 is sometimes described as a quasar, short for quasi-stellar radio source. When astronomers first detected quasars in the mid-20th century, they appeared as single points of light, like stars. But their spectra told a stranger story. The light was redshifted far beyond what any star could produce. These were not nearby objects. They were ancient, distant, and incredibly powerful. Quasars are the visible signatures of black holes in the act of devouring matter, and TON 618 is one of the most extreme examples ever found. If you could see it up close, ignoring for a moment that no human or probe could survive the journey, it wouldn't look like a hole at all. It would look like a blinding disk of white-blue light, radiating outward with a brilliance thousands of times greater than the Milky Way. The black hole itself would remain invisible, buried in the centre of the glare. You wouldn't see the boundary line where light fails to return. Instead, you'd see the consequences of matter falling too far, too fast, torn apart into heat and radiation before disappearing forever. The surrounding region would pulse and shimmer, distorted by gravitational lensing as space-time itself bent the light around it. When we say TON 618 is bright, it's not just metaphor. The energy output is estimated at around 100 trillion times that of our Sun. Imagine every star in the Milky Way combined, then multiply that brightness 100 times over, all of that power coming from a single point. One black hole, one accretion disk, one relentless gravitational pull. And remember, what we see is only the faint remnant of light that's travelled for 10 billion years. In its own time and place, TON 618 must have been unimaginably luminous, blazing across its galaxy like a cosmic lighthouse. It's strange to think that something which consumes everything around it can also be the brightest beacon in existence. But this is how black holes make themselves known. Not by shining, but by the destruction they cause. Matter falling inward releases gravitational potential energy as it accelerates, and a fraction of that energy is converted into radiation before crossing the event horizon. In most astrophysical processes, efficiency is low. chemical reactions, nuclear fusion, even supernovae. But accretion around a black hole can convert up to 40% of the infalling matter's mass into energy. It's the most efficient engine in the universe. The light from TON 618 doesn't just tell us it exists, it tells us how much it's eating. By measuring its luminosity, astronomers can estimate its accretion rate, how much matter falls in per year. In TON 618's case, it could be devouring the equivalent of several suns each month. Not peacefully or evenly, but through a chaotic storm of radiation and magnetic turbulence. Each atom pulled toward that centre adds a whisper to the light we see, a story written in energy. For all its brilliance, the space around TON 618 would not look like daylight as we know it. The light there would be too intense to comprehend, streaming mostly in ultraviolet and X-rays. It wouldn't be visible to the human eye in any natural way. The glow would burn through sensors, blind cameras, and vaporize anything close. Yet through the vacuum of space, that radiation stretches and fades until it becomes a faint shimmer detectable by radio telescopes on Earth. The violence of its creation is tempered by distance and time, arriving to us as a ghost of brightness. The idea that something so destructive can create such beauty is a recurring theme in astrophysics. Stars are born in chaos and die in explosions. Galaxies collide and merge, scattering dust that eventually forms new worlds, and black holes, though often described as the universe's devourers, play a crucial role in regulating galaxies. They shape star formation by heating and dispersing gas. Without them, galaxies might collapse too quickly or grow without structure. In their balance of destruction and creation, they keep the cosmos dynamic. TON 618 operates on a scale that makes our own galaxy's black hole seem tame. Sagittarius A, at the Milky Way's centre, has about 4 million solar masses. TON 618 is roughly 16,000 times heavier. That difference isn't just numerical, it's physical. Its event horizon, the region beyond which nothing escapes, would span about 390 billion kilometres across. If you could travel at the speed of a light, it would take you over a day to go from one side to the other. Inside that boundary, time and space no longer behave separately. Gravity becomes so intense that time slows relative to the outside world, stretching moments near the horizon into eternity. From far away, the light around TON 618 flickers slightly, like a candle through a lens. These flickers tell astronomers about turbulence in the accretion disk. The bright regions shift as gas spirals inward, orbiting at speeds close to light. The inner edge of the disk completes an orbit in mere hours, releasing more energy in that time than our Sun emits in a year. The geometry of that motion, circular, distorted, bent by gravity, shapes the light curve that telescopes detect. From those patterns, scientists infer the structure of the disk and the spin of the black hole itself. Spin, in black hole physics, is not just rotation. It's angular momentum encoded in space-time. A spinning black hole drags the fabric of space with it, twisting light and matter into spirals. This phenomenon, called frame dragging, means that near TON 618, even empty space is moving. Anything caught close enough is forced to orbit, not by choice but by geometry. The faster the spin, the more energy can be extracted from the disk and the jets that erupt from the poles. TON 618's immense brightness hints that it spins rapidly, channeling magnetic fields into beams that could stretch across intergalactic distances. Those beams, though invisible to human eyes, are real structures. They pierce through surrounding gas, carrying energy and charged particles far beyond the galaxy's edge. In some quasars, these jets are so powerful they influence the formation of neighbouring galaxies. TON 618's jets, if mapped in full, might span millions of light-years. Each one is a cosmic power line, connecting the black hole's rotation to the wider universe. When you think of all this happening 10 billion light-years away, there's a strange comfort in it. The violence is distant. The light is old. We're seeing the past replayed on the cosmic stage. a performance that ended before our planet existed. In that sense, TON 618 isn't just an object. It's a memory, preserved in light, replayed through our instruments. Its energy still touches us, though its present self may have changed beyond recognition. Perhaps it has quieted, consumed its surroundings, and now rests as a dark core at the centre of a dead galaxy. Or perhaps it still shines, unseen, its light still travelling toward worlds yet to form. The phrase, "where darkness shines brightest," feels less like poetry and more like physics. The glow around a black hole isn't a contradiction, it's a consequence. Gravity, in pulling matter inward, forces energy outward. The darker the centre, the more brilliant the halo. It's a natural trade, a balance of opposites that sustains the cosmic cycle. The same principle operates in nuclear fusion, supernovae, and even life itself. Pressure creating heat, destruction leading to light. TON 618 is just the grandest version of that rule, scaled to galactic proportions. What makes black holes such mesmerising subjects is how they warp everything familiar. Distance, time, motion, and even causality lose their everyday meaning. Light that should travel straight instead curves back on itself. Time that should pass evenly slows to a crawl. For an observer far away, the final fall of matter into a black hole appears frozen, never quite crossing the horizon. To the matter itself, the journey is brief, a plunge into nothing, completed in moments. The two perspectives are both true, coexisting in relativity's strange geometry. TON 618 amplifies that strangeness a billionfold. Astronomers often describe quasars like TON 618 as cosmic lighthouses, but that metaphor only captures part of their story. A lighthouse is built to guide, to warn of danger. TON 618's light does something similar, though unintentionally. It guides our understanding, showing us the limits of physical law. The photons it emits trace the path of matter under extreme conditions, letting us test theories of gravity, magnetism, and thermodynamics. Every observation tightens the link between mathematics and reality. In a way, TON 618 is not just a distant object, but an experiment conducted by nature itself, one that we happen to be able to read. It's easy to forget, lying here in a quiet room or listening on a calm night, that the universe contains such ferocity. Yet, in the same breath, that realization brings peace. Because for all its violence, TON 618 exists in equilibrium. It consumes, it radiates, it endures. Its light travels across expanding space, softening into a faint signal. That faintness is part of its story, a reminder that even the greatest powers in the cosmos eventually fade into background noise. But that fading light is enough for us to see, to wonder, and to learn. The next time you look up at the night sky, you might see a faint glimmer from a distant galaxy. Behind one of those points of light could lie another black hole, smaller perhaps, but following the same dance. Darkness wrapped in light, energy born of gravity. TON 618 just happens to be the loudest in that silent symphony, the one whose brightness outlasted the ages and reached us across the gulf of time. When scientists study quasars like this, they use every wavelength available: radio, infrared, optical, ultraviolet, X-ray. Each reveals a different layer of the story. Radio telescopes trace the jets. Optical telescopes measure the emission lines of hydrogen. X-ray observatories capture the innermost regions of the accretion disk, where temperatures soar to tens of millions of degrees. By combining these signals, researchers build a composite image, not of what TON 618 looks like to the eye, but of how it behaves, breathes, and evolves. Even after decades of study, questions remain. How did it grow so large in so little cosmic time? Was it born big, or did it feed with unusual efficiency? Did it form from collapsing primordial clouds, untouched by stars, or from a chain of mergers in an early chaotic galaxy? Each hypothesis leads to new simulations, new telescopes, new nights spent staring at data that might, just might, carry a clue. In that way, TON 618 is both an object and a challenge, an open question written across 10 billion years of light. And still, beyond the data and the math, there's the simple human feeling it evokes, a mix of awe and calm, a quiet recognition that the universe is far older and larger than anything we can measure, yet somehow knowable. That we, small beings made of the same atoms that once glowed in those distant disks, can look out and understand even a fraction of it. The brightness of TON 618 isn't just in photons, it's in the knowledge it brings, a light that reaches not just our eyes, but our sense of place. Somewhere out there, the energy it released is still moving, still expanding, still illuminating regions of space we'll never see. Every second, those waves spread a little farther, touching galaxies beyond our horizon, fading but never truly gone. That's what makes the idea of darkness shining so powerful. It's a reminder that the universe is never entirely still, never completely silent. Even the deepest black hides a pulse of light waiting to be found. The light that reaches us from TON 618 began its journey before Earth had oceans, before the Milky Way looked anything like it does now, before even our sun existed to cast daylight across this planet. When we observe it through a telescope, we're not just looking far into the distance, we are looking backward through the fabric of time itself. Every photon that reaches our instruments is an ancient traveller, a messenger from an era when the universe was still young, when galaxies were just learning how to organise themselves from clouds of hydrogen and helium. That's the strange truth about astronomy. When you gaze at the night sky, you're never seeing the present. You're looking at memories, frozen in light. The moon's glow is a reflection from 1 second ago. The light from the nearest star, Proxima Centauri, began its trip over 4 years ago. The light from the Andromeda Galaxy started out more than 2 million years ago, long before humans existed to notice it. And the light from TON 618, that faint signal captured in our detectors, has been travelling for more than 10 billion years. It left its home galaxy when the universe was roughly 3 billion years old. That means most of cosmic history, the entire span of everything familiar to us, has unfolded in the time that light has been moving across space. Try to picture that journey, not as an abstract number, but as a path. Imagine a single beam of light leaving the bright edge of TON 618's accretion disk, passing through its host galaxy, escaping its gravity, and entering the immense gulf of intergalactic space. For billions of years it travels unhindered. Galaxies form and drift apart. Stars are born and die in cycles. Entire civilizations could rise and vanish, and that single photon would still be on its way. No collisions, no rest, no slowing down. Just steady, silent movement through expanding space. But that space is not static. The universe itself has been stretching since the Big Bang. As space expands, so does the wavelength of the light moving through it. That's why the light from TON 618 is redshifted. The expansion of the universe has stretched its original ultraviolet radiation into visible and infrared wavelengths. By measuring that redshift, astronomers can determine how far the light has travelled and how long ago it was emitted. In TON 618's case, the redshift is about 2.2, meaning the universe has expanded more than threefold since those photons left. It's not just distance we're measuring, it's history. What's astonishing is how consistent that light remains despite everything it's endured. Over 10 billion years, through countless gravitational fields, through dust, gas, and cosmic microwave background radiation, enough of it still arrives to be measured, to draw spectra, to extract data. It's a testament to how persistent light can be. We think of it as fragile, easily blocked, easily lost, yet in reality it's one of the most durable messengers in existence. Once released, a photon can cross the cosmos without aging, carrying with it the imprint of its birthplace. When astronomers analyse the light from TON 618, they are, in a sense, decoding a fossil. They separate it into wavelengths using spectrographs, breaking it down into its constituent colours. Each element in the accretion disk leaves a unique fingerprint, a set of absorption or emission lines that reveal its composition and motion. Hydrogen, helium, carbon, oxygen, all of them etched into the spectrum like ancient hieroglyphs. The redshift tells us how far the light has travelled. The brightness tells us how much energy the black hole was releasing. Together these clues form a picture not of what TON 618 looks like now, but what it was like when that light was born. This is one of the most mind-bending aspects of astronomy. We can't observe the universe as it currently is. We only see it as it was. TON 618, as we see it today, might not even exist in the same form anymore. It could have quieted, its fuel exhausted, its glow faded. Its host galaxy may have merged with another, reshaping its structure completely. The light that tells us about it is a photograph from the deep past, arriving long after the scene has changed. Every star we see in the sky shares this quality. Each one is a message delayed by distance. The idea that we live surrounded by ancient light changes how you think about time. The stars are not above us in the present. They are scattered across the timeline of the cosmos. Some are newborn, some are long dead, but all are visible to us together in one tapestry of light. In that sense, the night sky is an illusion, a map of what was, not what is, and yet it's a beautiful illusion, one that lets us touch the deep past with our eyes. TON 618's light is especially significant because it tells us what the universe looked like when it was still assembling itself. 10 billion years ago, galaxies were smaller, denser, and more chaotic. Star formation rates were higher. Collisions were common. Quasars like TON 618 were more abundant because black holes were actively feeding, drawing in matter as the cosmic web thickened. These luminous objects served as cosmic lighthouses, visible from the earliest epochs. They help astronomers trace the growth of structure, the distribution of matter, and the evolution of the universe itself. When we observe TON 618, we're effectively studying the conditions that led to galaxies like our own. Its light shows how matter behaved under extreme gravity in the early universe. It reveals the chemistry of primordial gas clouds and the rate at which black holes grew. Each data point adds to a broader understanding that the universe has always been dynamic, evolving from simplicity toward complexity. What makes TON 618 stand out even more is the sheer improbability of its existence at that time. A black hole that massive shouldn't have had time to form in such a young universe, at least not according to our standard models. It challenges our assumptions about how fast black holes can grow. Either it was born unusually large, perhaps from the direct collapse of a massive gas cloud, or it found a way to feed far more efficiently than expected. The light we see today carries hints of that process, encoded in its spectrum waiting to be interpreted. It's remarkable how much information light can hold. A single photon has no mass, no charge, no rest frame, and yet it can tell us about gravity, motion, and temperature. It can cross billions of years without losing identity. It's the perfect messenger, immune to time's erosion. When you look up at the sky and see starlight, you're witnessing the same phenomenon on a smaller scale. The photons hitting your eyes left their stars years or centuries ago, and in that instant of arrival, they complete a journey that began long before you existed. TON 618's photons do the same, but on a cosmic timescale. The act of observing them connects us to that immense continuum. It's easy to forget that our ability to perceive light is what ties us to the universe. Every bit of knowledge we have about the cosmos comes from light, whether visible, radio, infrared, or X-ray, or we've built instruments that can catch it, stretch it, translate it, and turn it into understanding. Light is the language of the universe, and TON 618 speaks in that language at its loudest volume. Even after 10 billion years, the message it sends is coherent. It says that the universe was already complex, that black holes had already reached enormous sizes and that gravity had already begun shaping the large-scale structure we see today. The light carries with it not just information, but a sense of continuity. It links the present to the past, showing that everything that exists now was built upon what came before, layer by layer, wave by wave. If you were to stand somewhere in that galaxy 10 billion years ago near Ton 618's glare, the sky would look completely different from the one we know. The Milky Way wouldn't exist yet. The nearest galaxies would be closer, smaller and younger. The airless space around you would be filled with radiation from newly formed stars. In that ancient light, the seeds of everything we now know were already there. The atoms that would one day form you were being forged in the cores of stars just beginning to shine. That connection is not metaphorical, it's literal. The elements in your body were once part of the same universe that produced Ton 618's light. Over the eons, that light spread and dimmed, crossing cosmic distances that are difficult to express in human terms. A light year is the distance light travels in a year, about 9.46 trillion kilometres. Multiply that by 10 billion, and you begin to understand the scale. The number becomes so large it loses meaning. Yet, even at that unimaginable range, we can still measure it. That's the power of human curiosity paired with technology. To detect a signal so faint that it's just a few photons per second, and to turn it into knowledge about an entire galaxy. It's worth pausing on how extraordinary that is. The light from Ton 618 arrived here not because it sought us, but because that's what light does. It moves outward in every direction, filling space evenly. We just happen to build the right tools to catch a fraction of it. In a way, every observation is an accident of alignment, a brief overlap between our place in the universe and the path of something ancient. The fact that we can recognise that alignment, that we can look at a point of light and say, that's a black hole 10 billion years old, speaks to something remarkable about human perception. Even though Ton 618's light is ancient, it's not static. As it travelled, it was altered by the expansion of space, stretched in wavelength, diluted in intensity. What began as ultraviolet radiation is now deep red or infrared. That stretching carries information about the rate of expansion itself, about the cosmological constant, about dark energy. In studying old light, we study the very growth of the universe. Ton 618's photons are part of that record, tiny messengers that reveal the speed of cosmic evolution. There's a humbling symmetry in that. The oldest light in the universe, the cosmic microwave background, tells us about the moment when atoms first formed, about 380,000 years after the Big Bang. Ton 618's light comes from billions of years later, when structure had emerged. By comparing these signals, astronomers trace how matter assembled, how galaxies clustered, and how black holes like Ton 618 came to dominate the centres of those galaxies. Every observation fits into that broader timeline, a history written not in words, but in light. When you think about it long enough, you realise that the light from Ton 618 is not just old. It's older than memory, older than the ground beneath us, older than the molecules that make life possible, and yet it's here, reaching us now, touching the modern world of electricity and technology, bouncing off mirrors and detectors built by human hands. The connection between such different scales, and cosmic and personal, is what makes astronomy so powerful. It reminds us that our curiosity, small as it seems, is part of the same process that creates galaxies and stars. It's the universe becoming aware of itself through observation. If you ever find yourself outside on a dark night, far from city lights, look at the faint glow of the stars and remember that what you see is history arriving. Some of those photons began their trip when humans first lit fires, some when dinosaurs walked, some when Earth was still molten. Ton 618's light, invisible to your eyes but captured by telescopes, is a reminder that time and space are intertwined. To see across the universe is to see into the past, and to understand that even though we exist for a brief moment, We are part of a story that began long before and will continue long after. That light, ancient and patient, outran everything. Expansion, distance, decay. It crossed a universe that itself was growing and changing. It's not poetic exaggeration to say it outran time, because in the way physics works, photons do not experience time as we do. For a photon, from emission to absorption, no time passes. From its perspective, the moment it left TON 618 and the moment it struck a telescope are the same instant. To light itself, there is no journey. To us, there are 10 billion years. That contrast between what is and what is perceived is one of the most beautiful and strange facts of the universe. So when astronomers say they've seen TON 618 as it was 10 billion years ago, what they really mean is that they've received light that never aged. It's our universe that changed around it. The space expanded, galaxies moved apart, stars were born and died, and that light simply kept going, unbothered, until it met us. It's a silent, perfect record of endurance. And as that light continues to reach us, even now, it invites us to keep looking deeper. Beyond the brightness of TON 618 are countless other quasars, each one sending its own message from the past. Together, they weave a map of the early cosmos, showing where matter gathered, where gravity ruled, and where the first seeds of structure took hold. Each new discovery adds another point to that vast pattern, another reminder that we live in a universe still filled with echoes from its youth. The light from TON 618 may be ancient, but it's not finished teaching us. Every new telescope, every new method of analysis refines our understanding, revealing more about what happened in those first cosmic epochs. And as we continue to collect those photons, we keep piecing together a story that stretches beyond time as we know it. A story still unfolding in the faint glow that crosses the endless dark. When astronomers first estimated the size of TON 618, they had to double-check their calculations. The numbers seemed too large to be real. 66 billion times the mass of our Sun was not a figure anyone expected to find. Even in a universe known for extremes, this one stood apart, an object so enormous that it tested the limits of understanding. The term supermassive black hole already describes something difficult to imagine, but TON 618 requires an even greater leap of thought. It's not simply large, it exists on a scale that breaks the ordinary meaning of measurement. To appreciate what that truly means, it helps to start small, with something familiar. Our Sun, that steady sphere of nuclear fire, contains about 99.8% of all the mass in our solar system. It's vast enough that you could fit over 1 million Earths inside it. Its gravity holds planets in orbit across billions of kilometres. Now imagine multiplying that mass 66 billion times. That's TON 618. Its gravitational reach is not confined to a few planets, but could encompass entire star systems stacked one inside another like nesting dolls, each one swallowed without resistance. If TON 618 were placed at the centre of our solar system, its event horizon, the boundary where light itself cannot escape, would extend beyond the orbit of Neptune. The entire solar system would fit comfortably inside its invisible edge. The black hole's diameter would be nearly 400 billion kilometres. To cross that distance at the speed of light would take more than a full day. In comparison, light takes just over 8 minutes to reach Earth from the Sun. That scale difference is staggering, and yet it's only a number until you imagine what it represents. Inside that radius, gravity becomes absolute. No force, no technology, no energy can pull anything back once it crosses the event horizon. The black hole's escape velocity, the speed needed to break free from its pull, exceeds the speed of light. Nothing moves faster than that, so nothing escapes. This isn't a surface in the normal sense, but a boundary in space-time itself, a place where direction loses meaning. TON 618 doesn't have an edge you could touch. It has a point where the geometry of reality simply changes. The core of the black hole, the singularity, is a region where density and curvature become infinite, at least according to the equations of general relativity. Whether that infinity truly exists or whether it signals the breakdown of our mathematical models is still an open question. What's clear is that near the singularity, all known physics collapses. Space and time fold into one another, and the distinction between past and future blurs. For something as large as Ton 618, that inner mystery scales up as well, not just in size but in consequence. It's a place where gravity defines everything, and where understanding stops. Astronomers can't observe the singularity directly, but they can infer its presence from the behaviour of its surroundings. The enormous accretion disk orbiting Ton 618 glows with the energy released by matter falling inward. The faster the spin and the stronger the gravity, the hotter and brighter that disk becomes. By studying its spectrum and motion, scientists can estimate both the mass and the spin of the black hole. Ton 618's luminosity suggests that it is accreting matter near what's called the Eddington limit, the balance point between gravitational pull and the outward pressure of radiation. At that limit, the inflow of gas produces so much light that the radiation itself pushes back against the falling matter. Ton 618 sits delicately on that edge, a cosmic engine running at maximum output. Even at that balance, its appetite is immense. It consumes the equivalent of thousands of Earths every year. Yet it doesn't grow smoothly or quietly. Accretion is turbulent. Magnetic fields twist through the disk, forming hotspots where energy surges and fades. Material spirals inward unevenly, creating flickers of brightness visible even from billions of light years away. Those fluctuations give astronomers a glimpse into the black hole's feeding habits, like watching the heartbeat of a monster through its glow. For a sense of comparison, consider the black hole at the centre of our galaxy, Sagittarius A. It's about 4 million solar masses, enormous by any human measure, but a mere ember next to Ton 619's fire. Sagittarius A would fit into Ton 619's event horizon tens of thousands of times over. Our own galactic core is quiet now, barely accreting any matter. Ton 618, on the other hand, is caught in an active phase, radiating energy across the universe. The two objects belong to the same family, but they live in entirely different realms of power. What's fascinating is that black holes don't actually have a maximum size limit in theory. They can continue growing as long as they have material to consume. Galaxies feed them through collisions, mergers, and the steady inflow of gas. Over cosmic time, these processes allow a black hole to gain mass far beyond what we might intuitively expect. Ton 618 might have formed early, grown quickly, and merged with other black holes during the universe's youth, when galaxies were closer together. Each collision would have doubled or tripled its mass, and with enough time, the result would be this colossal entity we now measure. Still, the sheer rapidity of its growth raises puzzles. The early universe wasn't supposed to produce such giants so soon. Theoretical models of galaxy formation struggle to explain how black holes could reach billions of solar masses in less than 1 billion years after the Big Bang. For Ton 618 to exist at 10 billion light-years away, it must have achieved its current mass astonishingly quickly. That means either our understanding of early star formation is incomplete, or something unusual happened. Perhaps an era of super-efficient accretion, or the existence of massive seed black holes that formed from collapsing primordial gas clouds instead of stars. To appreciate the energy involved, think of Einstein's equation, E mc2. Even a small amount of mass produces a huge amount of energy when converted. Ton 618 converts vast quantities of infalling matter into radiation, releasing energy equivalent to millions of supernovae every second. The radiation pressure near its disk is so intense that it sculpts the surrounding galaxy, blowing away gas and halting new star formation in its immediate vicinity. This feedback process, as it's called, is one reason why galaxies and their central black holes seem to grow together. The black hole regulates the environment, preventing runaway starbirth and keeping the galaxy in balance. The scale of TON 618 makes it more than an isolated phenomenon. It's a structural component of the universe itself. Its gravity influences the motion of billions of stars within its galaxy. The energy from its jets and radiation affects regions of space millions of light years away. In a sense, TON 618 is not just in its galaxy. It is its galaxy's core identity. The relationship between a supermassive black hole and its host galaxy is deeply interdependent. Each shapes the other over cosmic timescales. To visualize its proportions, imagine the Milky Way as a vast city of stars. At its heart lies a central plaza, Sagittarius A. TON 618, by contrast, would be like an entire continent condensed into a single intersection. The gravitational well it creates would dwarf everything around it. Its presence would define the motion of every star, every cloud of gas, every orbiting object. If we could somehow visit its galaxy, we would see a bright, compact centre surrounded by a halo of stars and dust, all slowly circling a point that could never be approached. But there's another dimension to TON 618's immensity that numbers can't capture: its effect on time. According to general relativity, gravity and time are inseparable. The stronger the gravity, the slower time passes relative to regions farther away. Near TON 618's event horizon, a second could correspond to years or even centuries for an outside observer. To something orbiting close to its edge, time itself would stretch, dilating under the weight of space-time curvature. If you could hover safely just outside the horizon, the rest of the universe would seem to race forward, while your own clock slowed almost to stillness. The deeper the gravity well, the greater the distortion. TON 618's gravity is so extreme that its time dilation effects would be profound, an unbridgeable difference between its vicinity and the wider cosmos. Light near that horizon doesn't behave as we expect either. Photons that escape must climb out of the gravitational field, losing energy as they do so. That's why the regions near the event horizon appear redshifted. The light stretches, its frequency lowers, its colour fades as it fights to escape. To a distant observer, the innermost edge of the disk seems to move in slow motion, its glow dimmed by gravity's grip. This is not just theory. It's been confirmed by observations of closer black holes, like the one imaged by the Event Horizon Telescope. TON 618's scale simply magnifies the same principles to an almost incomprehensible degree. Even though we can't photograph TON 618 directly, it's far too distant for current instruments, we can infer its characteristics through careful modelling. The shape of its spectrum, the velocity of its emission lines, and the luminosity of its quasar all point to its staggering mass. Each measurement reinforces the picture of a black hole at the uppermost limit of what nature has so far revealed. If there are larger ones, they remain hidden, perhaps obscured by dust or inactive, after consuming all nearby matter. TON 618 is the one that still speaks through its light, announcing its presence across space. It's interesting how something defined by invisibility can still dominate the observable universe. The paradox lies at the heart of why black holes capture our imagination. They are boundaries between the known and the unknowable. TON 618's enormity doesn't just stretch the limits of physical measurement, it stretches the limits of comprehension. We can describe it, calculate it, simulate it, but we can't truly picture it. Our minds evolve to grasp trees, mountains, horizons, not objects that rewrite space-time on galactic scales. Yet we persist in trying, because the effort to imagine is part of what makes us curious creatures. Perhaps that's why black holes inspire both fear and fascination. They represent the edge of what's possible, places where nature hides its deepest truths. TON 618 in particular sits at that edge like a monument to cosmic scale. It's not evil, not sentient, not consuming for the sake of destruction. It simply is, A structure formed by gravity doing what gravity does best. In that simplicity lies its grandeur. The universe builds complexity out of simple rules repeated endlessly. Gravity pulls, matter falls, energy radiates. Repeat that long enough, and you get galaxies, stars, planets, and eventually something like Ton 618. If you think of the universe as a story, then Ton 618 is one of its most dramatic chapters, an example of what happens when those simple laws are allowed to run unchecked. There's no intention behind it, no goal, yet the result feels purposeful in its scale, almost architectural. Its gravity sculpts the space around it, its light reveals the history of the early cosmos, and its continued existence challenges our models of how fast the universe can evolve. Even its name, Ton 618, feels clinical, like a catalogue entry rather than a cosmic wonder. It comes from a survey designation, a label assigned without flourish. But behind that sterile name lies something beyond imagination. Sometimes science's understatement adds to the sense of awe, the idea that we can compress the vastness of a 66 billion solar mass black hole into 3 characters and a number. It's both humbling and strangely fitting. The universe doesn't need grandeur in naming. The grandeur is built into the thing itself. In the end, Ton 618 stands as a reminder of how scale can defy understanding, but still invite reflection. It asks no questions and gives no answers, but it embodies the forces that govern everything, from the orbit of electrons to the expansion of galaxies. Its light, born of destruction, crosses the ages to show us what gravity can make. And though we may never see it directly, its existence is written into the data, into the subtle flicker of photons that reached us after 10 billion years. As we follow its trail, we find ourselves not at the end of the story, but at another beginning, where the question shifts from how large it is to how such enormity came to be. Somewhere in that transition, between understanding and wonder, lies the heart of what it means to study the cosmos. Because to comprehend Ton 618, even partially, is to confront the scale of the universe itself, not as something distant, but as the context in which we quietly exist. And as our instruments grow sharper and our eyes turn deeper into the void, we will keep searching for others like it, more colossal, more distant, more revealing. Because each discovery, no matter how overwhelming, brings us one small step closer to knowing how something so vast could emerge from the same physics that binds the atoms in our hands. To understand something as immense as Ton 618, it helps to remember that even the most colossal structures begin small. Nothing in the universe starts fully formed. Every star, every planet, every galaxy is the result of accumulation, of countless small pieces coming together over time. Black holes are no different. They are, in essence, the ultimate expression of gravity's appetite, a slow, relentless consumption of matter that never stops as long as there is something nearby to devour. When we talk about how black holes grow, we're really talking about how the universe feeds its own extremes. At their simplest, black holes begin with the death of stars. When a massive star exhausts its fuel, the outward pressure from nuclear fusion collapses and gravity takes over completely. The star implodes, crushing its core into a point of infinite density, a singularity. If the remaining mass is large enough, not even the explosive force of a supernova can stop it. The result is a black hole, a region of space from which nothing can return. Most of these stellar black holes are just a few times heavier than our Sun. On their own, they are small, quiet, almost invisible. But given enough time and enough matter to consume, they can become something far greater. The process of growth begins when a black hole encounters a source of fuel, gas, dust, or stars that stray too close. The gravity of the black hole pulls this material inward, but rather than falling straight in, it forms a disk. That disk, the accretion disk, is where the real drama happens. As matter spirals closer, it compresses and heats to extraordinary temperatures, radiating energy in the form of light and X-rays. This energy is what we see when we observe quasars like TON 618. The black hole itself remains hidden, but its meal gives it away. The physics of accretion are deceptively simple. Gravity pulls matter inward. Friction within the disk slows it down, converting motion into heat. That heat produces radiation, which pushes outward. The balance between these two forces, gravity drawing in, radiation pushing out, determines how fast the black hole can grow. Too much radiation, and the pressure will drive material away before it can fall in. Too little, and the process becomes unstable. TON 618, based on its brightness, appears to operate close to the Eddington limit, the point where inflow and outflow reach equilibrium. It's eating as fast as physics allows. But black holes don't always eat politely or steadily. Their meals are chaotic, governed by turbulence and chance. In the dense centres of young galaxies, gas clouds collide, stars wander, and everything is in motion. Sometimes two black holes merge, doubling their mass in a single event. Other times, one finds itself in the aftermath of a galactic collision, surrounded by new fuel. In those moments, the growth becomes exponential. Each addition of mass strengthens gravity, making it even easier to draw in more matter. It's a self-reinforcing process, one that can transform a modest black hole into a supermassive one over cosmic time. For TON 618 to have reached its staggering size, it must have undergone several of these feeding cycles early in the universe's history. Its host galaxy likely formed through mergers, smaller galaxies combining, their central black holes merging too. Each merger triggered new waves of star formation, new flows of gas, and new opportunities for accretion. The black hole at the centre, once small, became the gravitational anchor around which the galaxy organised itself. By the time the light we see today was emitted, TON 618 had already become a cosmic giant, consuming matter at a rate that defies intuition. Feeding, however, comes with consequences. The energy released during accretion doesn't simply vanish. It radiates outward, affecting everything around it. In the most extreme quasars, the radiation is so intense that it can push away surrounding gas, effectively starving the black hole for a time. This feedback mechanism helps regulate growth. Too much accretion leads to too much radiation, which then drives away the fuel. Too little, and the black hole begins to fade. In this delicate balance, the black hole and its galaxy find a kind of equilibrium, each shaping the other's evolution. The image of a black hole as a gluttonous monster devouring everything nearby is not entirely accurate. While it's true that nothing can escape once it crosses the event horizon, the vast majority of matter around a black hole never reaches that point. Much of it orbits, collides, or gets ejected by powerful jets. In TON 618's case, these jets likely stretch thousands of light years into space, spewing charged particles at nearly the speed of light. They are byproducts of the same magnetic and rotational forces that power the accretion disk. Through these outflows, black holes return some of their energy to the universe, seeding into galactic space with heat and momentum. It's almost ironic that the act of consuming can create. The energy released by black hole accretion can trigger the formation of new stars in surrounding regions. Shock waves compress gas clouds, igniting fusion in places where it might not have occurred otherwise. The result is a cycle of destruction and creation, matter falling in, energy pouring out, new structures forming from the debris. TON 618 is a perfect example of this duality. Its brightness comes from annihilation, but that light travels across the universe to illuminate new worlds, new telescopes, new minds. When scientists model black hole growth, they consider several pathways. The first is direct accretion, the slow, steady feeding from surrounding gas. The second is mergers, two black holes combining their masses. The third involves super-Eddington accretion, where the inflow temporarily exceeds the theoretical limit. In some cases, black holes may gulp down matter faster than radiation can push it away, leading to bursts of rapid growth. The exact conditions required for this are still debated, but in the dense, chaotic environments of early galaxies, it's entirely possible. TON 618's immense size suggests that such processes played a role in its formation. What's remarkable is that even at its most extreme, black hole feeding follows predictable laws. The equations that describe how matter spirals inward are the same equations that govern accretion disks around young stars. Nature repeats patterns at every scale. The difference lies in energy and scale, not in principle. A black hole feeding on a star's remains follows the same physics as a protoplanetary disk forming worlds: gravity, motion, heat, and balance. It's the same universe, expressing itself through different magnitudes. If you could observe TON 618 up close, you wouldn't see chaos in the human sense. You'd see order born from physics. The gas in the accretion disk follows elegant elliptical paths. Its temperature increases smoothly toward the centre. Its radiation obeys precise spectral laws. The light we see, faint and ancient, is a product of those interactions, predictable, measurable, and astonishingly consistent across billions of years. In the grand design of things, even destruction obeys symmetry. Over cosmic timescales, black holes grow, feed, and sometimes go dormant. When their surrounding galaxies run out of gas, accretion slows, and the bright quasar phase ends. The black hole remains, but without fuel, it becomes invisible again, detectable only through its gravitational influence. TON 618 may one day reach that stage, if it hasn't already. The light we see today shows it at its most active, but 10 billion years later, it may be silent, its glow long faded. The energy that once blazed like a beacon will have dispersed, leaving behind only the memory carried by photons now drifting past our detectors. Despite their terrifying reputation, black holes are surprisingly efficient at conserving the universe's balance. They don't hoard matter forever. The energy they emit during feeding helps distribute material across space, preventing galaxies from growing too dense. Without this regulation, the cosmos might look entirely different: overcrowded, unstable, less structured. The very existence of supermassive black holes like TON 618 ensures that galaxies evolve in an orderly way. They are not cosmic destroyers, but cosmic organizers. From a human perspective, it's tempting to think of this as purposeful, as though the universe designed black holes to maintain order. But there's no intention behind it. It's simply the outcome of gravity and thermodynamics working together over immense spans of time. Every atom that falls toward a black hole follows the path dictated by physics. Each collision, each burst of light, each jet of plasma is the result of cause and effect playing out across eons. The beauty lies in how those laws, so simple in form, create such staggering complexity. For astronomers, studying how black holes grow is more than an exercise in numbers. It's a way to understand how the universe builds itself. The mass of a galaxy's central black hole is closely correlated with the mass of the galaxy's bulge, the dense central region of stars. This relationship, known as the M-sigma relation, suggests a feedback loop. As the black hole feeds, it influences star formation, and as stars form and die, they return matter that can feed the black hole. Each depends on the other, bound in a cycle that spans billions of years. TON 618, at its extreme end, helps define the outer boundary of that pattern. The question that follows naturally is whether there is any upper limit. Could a black hole continue to grow indefinitely? In theory, yes, as long as it has something to eat. But in practice, the supply of matter is finite, and the universe itself is expanding. Over time, galaxies drift apart, and the fuel available to any given black hole diminishes. Eventually, even the largest ones will run out of food. When that happens, They will become quiet, cold, and eternal, influencing their surroundings through gravity alone. Ton 618's brilliance is temporary on a cosmic scale, a brief flare in an otherwise endless night. Still, while it lasts, it is among the most efficient engines ever known. A black hole converts a greater fraction of mass into energy than any other natural process. Stars convert about 0.7% of their mass through fusion. A black hole can convert up to 40% during accretion. That efficiency is what powers quasars, what lights up the distant universe, and what allows us to see Ton 618 at all. It's not hyperbole to say that black holes are the ultimate factories of light, even though they themselves remain dark. The more astronomers learn about them, the more they realise how central they are to cosmic evolution. Without them, galaxies might lack the structure we see today. Their presence determines where stars form, how long galaxies remain active, and how energy circulates on large scales. They are both the endpoints and the catalysts of matter. Every galaxy we know has one, and everyone tells a version of the same story, of growth, balance, and transformation through the act of consumption. When light from Ton 618's feeding disk reaches us, it carries all of that information encoded in its spectrum. It tells us how hot the gas was, how fast it was moving, how much energy was being released. It's as though the black hole leaves behind a diary written in radiation, waiting for anyone patient enough to read it. Each photon is a word, each wavelength a sentence, describing a process too vast for direct observation. The more we study that light, the clearer the story becomes. In the grand view, black holes like Ton 618 are not just consumers, they are recyclers. The material they expel through jets and winds eventually cools and becomes part of new galaxies, new stars and new planets. The same atoms that once swirled near its horizon could, billions of years later, become part of another system somewhere else in the cosmos. The cycle never ends. It only changes form. Even in destruction, there is continuity. And perhaps that's what makes the study of Ton 618 so compelling. It's not just about understanding how something grows so large, it's about realizing that growth itself is universal. The same principles that govern a black hole's feeding govern the birth of stars, the structure of galaxies, and even the chemistry of life. Gravity pulls things together, energy pushes them apart. Somewhere between those forces, existence finds its shape. As we trace the faint echoes of Ton 618's cosmic feast, we begin to see how everything in the universe is connected by that same exchange. Matter becoming energy, energy becoming light, light becoming knowledge. It's a process that's been happening for billions of years, and for a brief moment, through observation and curiosity, we get to be part of it. Deep within the glowing swirl of Ton 618's accretion disk lies something so strange that even science, with all its tools and mathematics, can only describe it partially. Everything we've discussed so far, the brightness, the heat, the jets of energy, all of that comes from the surroundings of the black hole. None of it comes from the black hole itself. At the very centre of that storm is silence, a place without sound, without light, without surface, without shape in any normal sense. That is the monster's heart. It's almost misleading to call it a thing. A black hole isn't an object like a planet or a star. It's a region, a distortion in space-time created by gravity so strong that it curves the geometry of the universe back on itself. The more mass that's compressed into a small space, the deeper that curvature becomes. For Ton 618, the curvature is so steep that light, which always moves in straight lines through space, finds itself following those curves inward. It can orbit the black hole several times before vanishing entirely. Once light passes the event horizon, it's gone forever, trapped in a region where all paths lead inward and none lead out. To imagine the heart of Ton 618 is to abandon familiar reference points. There is no solid surface to land on, no atmosphere, no material to touch. The event horizon isn't a physical boundary, but a mathematical one, a threshold marking where escape becomes impossible. To an outside observer, anything falling toward that boundary seems to slow down as it approaches, taking longer and longer to cross, its light redshifting into deeper tones until it fades entirely. To the infalling object, however, there's no pause. It crosses the horizon in finite time, descending toward the singularity at the centre. Both views are correct, depending on where you stand in space-time. That duality, two realities coexisting, is part of what makes black holes so difficult to comprehend. They twist the relationship between time and space, turning motion into geometry. Near the heart of TON 618, gravity doesn't just pull, it shapes the flow of time itself. The closer you get, the slower time runs relative to distant regions. If you could somehow hover near the event horizon, your clock would tick slower than one on Earth. In the extreme environment of TON 618, the difference would be so great that seconds for you could correspond to years, decades, or even centuries elsewhere. This isn't an illusion or a trick of perspective, it's a measurable consequence of Einstein's general theory of relativity. Time dilation near strong gravitational fields has been confirmed on much smaller scales, around Earth, around the Sun, even around neutron stars. TON 618 simply magnifies the same principle until it becomes surreal. If you could orbit just outside its event horizon, you could watch the universe outside fast forward, galaxies aging and dying in moments, while from the outside your motion would appear frozen in place. The black hole turns time into a one-way lens, where the direction of experience itself becomes relative. Inside the event horizon, all paths, even those that would normally lead outward, bend toward the singularity. It's not that space pulls things in, it's that the geometry of space-time itself curves inward. Once across that line, there's no force or speed that can counteract the descent. The singularity isn't a location in space, but a state of infinite curvature, where density becomes undefined. In TON 618's case, that singularity contains the mass of 66 billion suns crushed into a volume smaller than an atom. That phrase doesn't really make sense in everyday terms, because at those scales, space and matter cease to behave separately. The singularity is the end of our equations, a region where the known laws of physics break down. Physicists often say that the singularity marks the limits of our understanding, not necessarily the limits of nature. Something must exist there, some structure or process that current theories can't yet describe. Quantum gravity, the hypothetical framework that would unify general relativity and quantum mechanics, might eventually reveal what happens inside. For now, all we know is that TON 618's core represents the most extreme environment imaginable, where the density, temperature and curvature of space-time reach values beyond comprehension. If you could watch matter fall into it, you'd see something strange. As gas spirals inward through the accretion disk, it accelerates to nearly the speed of light. The friction between particles creates immense heat, which produces radiation. The closer it gets to the event horizon, the more energy it releases. Eventually that light can't escape either. To an observer far away, the infalling material seems to slow, freeze, and fade, never quite crossing the line. But that's only because the light from each successive moment takes longer to reach us. In the infalling matter's own frame, it crosses quickly, disappearing into a future from which no information returns. That inability to see inside doesn't mean nothing happens there. It means that what happens is hidden permanently. The interior of a black hole is causally disconnected from the outside universe. No signal, no particle, no photon can bridge the divide. Yet paradoxically, the black hole still interacts with the outside through its gravity. The mass it contains continues to shape the space-time around it, influencing the motion of stars, gas and light. In that sense, TON 618's heart is both sealed off and still connected, like a wound that never closes but continues to affect everything around it. The horizon itself is dynamic, not static. When the black hole consumes matter, the horizon expands. Its radius increases in proportion to the added mass. Over cosmic time, Ton 618 has likely grown in this way countless times, each new wave of infalling gas enlarging its gravitational boundary. The event horizon, though invisible, is a real physical feature, a surface where escape velocity equals the speed of light. Its size defines the black hole's scale. For Ton 618, that boundary is immense, far beyond what we can meaningfully visualize. It's also not perfectly smooth. On a quantum level, the event horizon might fluctuate, rippling with minute variations due to the effects of quantum uncertainty. Stephen Hawking's work suggested that black holes are not entirely black. They emit faint radiation through quantum processes near the horizon. This Hawking radiation is negligible for supermassive black holes, far too weak to detect. But in theory, it means that even Ton 618 could slowly lose mass over unimaginable timescales. The process would take longer than the current age of the universe multiplied by another universe's worth of time, but it's still a reminder that even the mightiest structures are not truly eternal. From the outside, Ton 618 appears as energy and motion, light, radiation, and gravity in perfect balance. From the inside, if we could somehow experience it, it would be pure geometry. No stable orbits, no escape, just a continuous fall toward a point that may not even exist in any classical sense. The notion of a centre becomes meaningless, because the curvature of space-time replaces location with inevitability. The deeper you go, the more the concept of space dissolves. That idea unsettles most people when they first encounter it. The notion of a place that isn't a place, of an object that contains nothing we can define. Yet that's what Ton 618 is at its heart, the manifestation of gravity's final form. It's what happens when matter's pressure can no longer resist collapse, when the equation balances only by bending space-time completely inward. Everything we see, the blazing disk, the jets, the radiation, are byproducts of this invisible geometry. In many ways, Ton 618's heart acts as a one-way membrane between the known and the unknown. The event horizon is the boundary of knowledge itself. Information can cross inward, but it cannot return. This leads to one of the great paradoxes in modern physics, the information problem. According to quantum theory, information about a system's state can never be destroyed. Yet if matter and light fall into a black hole and never come out, that information seems to vanish. For decades, physicists have debated whether it's truly lost or somehow encoded in subtle ways at the event horizon. Some propose that the horizon stores information holographically, smeared across its surface like data on a cosmic drive. Others think that quantum entanglement preserves it in ways we can't yet detect. Ton 618, by its sheer scale, magnifies this question to an extraordinary degree. Whatever the answer, it will reshape our understanding of the universe at its most fundamental level. The heart of Ton 618 also teaches something more philosophical about observation. No matter how powerful our instruments become, there are limits we cannot pass. The laws of nature themselves set boundaries on what can be known. The event horizon is not just a physical barrier, but an epistemological one, a reminder that knowledge has edges. Beyond those edges lies speculation, mathematics, imagination. The existence of such a frontier gives science its depth. Without limits, discovery would have no meaning. Even so, the region around the horizon is full of phenomena we can measure indirectly. The gravitational lensing caused by Ton 618 would bend light from background galaxies into arcs and rings. The X-rays emitted by its inner disk reveal the velocities of particles moving at relativistic speeds. The radio emissions trace magnetic fields coiled by rotation. Each of these signatures lets us map the invisible through its effects, turning absence into data. It's how astronomers reconstruct the unseen, one equation and one photon at a time. What emerges from those studies is a portrait not of chaos, but of elegance. TON 618's heart, for all its violence, is stable. It's governed by symmetry, spherical, predictable, consistent across time. It doesn't flicker erratically like a star, it endures. Its gravity is absolute but precise. Space curves smoothly into it, light follows defined paths, and energy radiates according to fixed laws. In the deepest sense, the monster's heart is not wild at all. It's the universe's most orderly creation, a perfect solution to Einstein's equations realized in nature. That perfection has a quiet beauty. The mathematics describing it are exact, clean, and deceptively simple. The Schwarzschild radius, the formula that defines the size of a non-rotating black hole, depends only on mass and fundamental constants. Double the mass, double the radius. The same equation applies whether the black hole weighs a few suns or 66 billion. TON 618's enormity doesn't complicate the math, it just scales it up. That's the strange harmony of the cosmos. Even at the extremes, the rules remain the same. If you could somehow drift near the event horizon and look outward, you'd see a distorted universe. Light from distant stars would bend around you, circling the black hole before escaping. The outside world would appear compressed into a bright ring surrounding darkness. The sky would seem to fold in on itself, a 360-degree view wrapped around your vision. And if you tried to look back toward the centre, you wouldn't see anything at all. Just blackness where geometry ends. It's not death or emptiness in any emotional sense. It's simply a place where our definitions of existence no longer apply. That's what makes TON 618's heart such a profound concept. It's a reminder that the universe is not obligated to be intuitive. Nature follows rules that we can uncover but not always visualize. A black hole's centre is not meant to fit comfortably within human imagination. It challenges the very idea of what place means, what inside means, what time means. Standing at the edge of that realization, one feels both small and oddly connected. Because even though we can't see inside, the same physics that created that heart governs everything around us. Perhaps the most astonishing thought is that, at its core, TON 618 is made of the same matter as everything else. The same hydrogen and helium that formed stars and planets, compressed beyond recognition. There's nothing exotic about its ingredients, only about its state. The universe uses the same materials everywhere. It's the conditions that change. Under enough pressure, matter itself becomes geometry, and geometry becomes destiny. The heart of TON 618 may be hidden forever, but its existence shapes everything we can see. Its gravity anchors its galaxy. Its energy fuels its brilliance. Its silence gives rise to light. In that balance between visibility and absence lies the essence of the cosmos. A world where the greatest forces are often invisible, and the most powerful truths are those we can only infer. And as we drift further into this exploration, deeper into the unseen, begin to recognise that the monster's heart isn't just a mystery to be solved. It's a reflection of how far knowledge can reach before it gives way to wonder. Because even in the centre of darkness there's structure. Even in the heart of gravity there's balance. The universe, vast and quiet, is never truly silent. Even the most distant corners hum with faint signals, whispers of energy that travel endlessly through the dark. Space may seem empty, but it's filled with waves, light waves, radio waves, gravitational ripples, all carrying stories from events that happened long ago. Every star, every quasar, every collision leaves a trace, a vibration that never quite fades. TON 618, though impossibly far away, contributes to that cosmic symphony. Its light, its radiation, and even the shape of its surrounding space ripple outward through the intergalactic sea, echoes of something that still stirs the universe. When astronomers speak of detecting TON 618, what they really mean is that they've caught its echo. Light doesn't arrive with a label attached. It doesn't declare its origin. It must be decoded, separated from the background, filtered, and analysed until its source becomes clear. The faint signals that reveal TON 618 began as invisible energy scattered across wavelengths, some in visible light, some in ultraviolet, some in radio. Over the course of billions of years, they've stretched and shifted as the universe expanded. By the time they reach our telescopes, they are little more than murmurs. Yet within those murmurs lies everything we know about one of the most powerful objects in existence. The first of these echoes came in the form of radio waves. In the middle of the 20th century, astronomers mapping the sky began to find strange points of radio emission that didn't match any known stars or galaxies. They were compact, bright, and often located in regions of deep space where no visible objects seemed to exist. These sources were called quasi-stellar because they appeared star-like through early telescopes. One of them, recorded at the Tonantzintla Observatory in Mexico, was designated TON 618. At first, it was just a name in a catalogue, one of many. Only later did scientists realise that these points were anything but ordinary, that they were the glowing hearts of distant galaxies, powered by supermassive black holes. The light from these quasars wasn't steady. It flickered subtly, changing over weeks, months, and years. That variability hinted at something small yet powerful, something compact enough for its entire brightness to fluctuate on such short timescales. A whole galaxy could not vary like that, but an accretion disk around a black hole could. The pattern of those flickers, the intensity of their radiation, and the redshift of their spectral lines all pointed to one conclusion. These were the echoes of feeding black holes, billions of light years away, blazing with energy as they devoured matter. To detect TON 618 today, astronomers use instruments that can see across many wavelengths. Radio telescopes capture the low-frequency hum of its jets. Optical observatories pick up the faint stretched light of its accretion disk. X-ray satellites, orbiting above Earth's atmosphere, record the high-energy radiation produced near its event horizon. Together, these signals form a composite portrait, each frequency revealing a different layer of the same phenomenon. What we call seeing a black hole is really an act of listening to all the wavelengths it sends us, combining them into a coherent story. This act of cosmic listening is one of humanity's quiet triumphs. The energy from TON 618 that reaches us is unimaginably weak, a few photons per square metre, per second, spread over an entire planet. Yet with carefully tuned instruments, we can detect it, measure it, and extract meaning from it. That faint glow has crossed more than 10 billion light-years to reach us, losing strength at every step but never losing coherence. It carries, encoded within it, the chemical fingerprints of hydrogen and helium, the speed of the gas swirling near the event horizon, and even the rotation rate of the black hole itself. Astronomy, at its core, is a science of patience and inference. We can't touch the things we study, can't bring samples from distant galaxies, can't peer directly into the heart of TON 618. All we can do is measure light, analyse its spectrum, and deduce what it means. From those deductions, entire worlds unfold. A few bright lines in a spectrum become evidence of an accretion disk millions of degrees hot. A slight shift in wavelength becomes proof of a receding galaxy. A faint flicker becomes the heartbeat of a black hole feeding in the dark. For TON 618, these echoes are especially powerful because of how far they've travelled. The farther the light, the older the story. Each signal from that region of space tells us not only what the black hole is, but what the universe was when that light began its journey. It's like hearing a voice from a time when the cosmos was still in its adolescence, full of turbulent energy and rapid growth. TON 618's echo isn't just about one object. It's about the early universe itself, when quasars were common and galaxies were young. When astronomers observe these distant echoes, they use a technique called spectroscopy, the study of how light is distributed across wavelengths. By spreading the incoming light into a rainbow of colours, scientists can identify specific patterns that correspond to elements and molecules. Hydrogen leaves one set of lines, helium another, and heavier elements like carbon and oxygen each add their own subtle imprints. The pattern of these lines tells us not only what's present, but how fast it's moving and in what direction. In TON 618's spectrum, these lines are shifted toward the red end, stretched by the expansion of space. From that shift, we calculate its redshift value, which in turn tells us its distance, about 10.4 billion light-years. Radio astronomy adds another layer to the picture. The jets that erupt from TON 618's poles emit radio waves that travel immense distances with little interference. These jets are formed by magnetic fields near the black hole's event horizon, twisted and wound by its spin. They launch particles at nearly the speed of light, projecting beams of plasma across space. When those beams interact with surrounding gas, they create radio lobes, vast, diffuse regions that can stretch for millions of light-years. By mapping these emissions, astronomers can trace the direction, speed, and power of the jets, building a three-dimensional model of TON 618's environment without ever seeing it directly. Even gravitational waves, ripples in space-time produced by massive movements, may one day carry echoes from TON 618's past. If it ever merged with another supermassive black hole, the resulting collision would have sent gravitational vibrations rippling across the universe. We haven't detected such signals from that far away yet, but future instruments might. Each new form of observation adds another sense to our perception, turning the silent cosmos into something we can almost hear. What makes these echoes so fascinating is how they persist. In a human lifespan, the universe seems static. Stars rise and set, constellations look the same year after year. But in cosmic terms, everything changes. Galaxies collide, stars explode, black holes feed and fade. The light from TON 618 we see now is a single frame in that vast motion, a still image frozen in transit. Somewhere in the present universe, TON 618's reality may be different. It could be dormant, quiet, or merged with another black hole. Yet its ancient light still speaks as though the past were alive. That persistence is part of what gives astronomy its contemplative quality. When we observe something like TON 618, we're not watching it happen. We're witnessing its echo. The event itself ended long ago, but the signal continues to travel, indifferent to time. Light doesn't remember when it was emitted. It just moves forward, carrying information until something absorbs it. We happen to be the absorbers, the receivers of that ancient transmission. Our telescopes are like nets catching the final photons of an event that occurred when the universe was young. In that sense, studying the echoes of black holes is an act of translation. We take something born of gravity and energy, convert it into light, then into data, and finally into understanding. The process connects us to phenomena that should be utterly beyond our reach. We cannot visit TON 618. We cannot send a probe or look directly into its heart, but through light we can reconstruct its story. Each observation adds detail to the portrait, filling in pieces of a puzzle that spans billions of light-years. The most humbling part is how small the signal actually is. When the photons that left TON 618 finally reach Earth, they've been stretched and weakened by time. They are individual quanta of energy, scattered among countless others from stars, galaxies, and cosmic dust. Yet, by gathering them patiently, we can separate them from the noise. A telescope doesn't see the black hole in the traditional sense. It collects its whisper. That whisper, multiplied by years of observation and refined through mathematics, becomes knowledge. It's the closest thing we have to hearing the universe think aloud. These echoes also reveal how connected everything in the cosmos is. The same space that carries light from TON 618 carries radiation from the cosmic microwave background, the afterglow of the Big Bang. The same vacuum that allows radio waves to travel also carries cosmic rays, neutrinos, and gravity itself. Each type of signal travels at its own scale and energy, but all share the same stage. The universe is not a void, but a medium filled with communication, every part resonating with the motion of everything else. The discovery of quasars like TON 618 changed how we think about that medium. Before them, the universe seemed mostly quiet beyond the Milky Way. Galaxies were known, but few imagined that their centres could outshine all their stars combined. The realization that these bright points were powered by black holes billions of light years away expanded not just our catalogue of objects, but our understanding of cosmic structure. It showed that even in the darkest regions, energy and motion persist. The echoes of TON 618, faint though they are, tell us that the universe is never still. Every signal we receive from it, every spectrum, every radio wave, every flicker of X-ray light contributes to a collective record, a memory of how the universe sounded at its most active. When we convert those signals into images, graphs and models, we're essentially tuning into a cosmic frequency, one that resonates across time. The black hole's roar, stretched and softened by distance, becomes a gentle hum of data. And within that hum lies the memory of creation itself, of matter transforming into light, of gravity shaping space, of the universe expressing its energy through form. Even the background noise in our detectors, the random fluctuations of radiation that fill the sky, holds meaning. Some of that noise comes from the edges of the observable universe, some from ancient stars, some from distant quasars like TON 618, whose signals have blended into the cosmic static over time. It's a reminder that silence in space is not emptiness, it's complexity stretched thin. In that way, the universe behaves like an ocean. Its surface looks calm from a distance, but beneath it are waves of every size and rhythm, each carrying a story of motion. TON 618 is one of the great storms in that ocean, a source of ripples that continue to spread across billions of light years. And we, tiny observers on a small planet, are sensitive enough to feel those ripples. We build instruments to measure them, we interpret their patterns, and we find meaning in their rhythm. The idea that we can detect something so distant, so ancient, from a quiet observatory on Earth might seem improbable, but it's a testament to how far human perception has reached. We've learned to amplify the faintest echoes and translate them into understanding. In doing so, we've turned the cosmos into a dialogue, not of words, but of waves. TON 618 speaks in that language, its message carried by light and energy across a sea that never ends. And so the echoes continue, faint but constant, threading through the universe like invisible currents. They remind us that even in the vastness of space, everything is connected through motion and time. The light from TON 618, the radiation from stars, the relic heat of the Big Bang, all of it mingles in the same expanse. We're surrounded by those echoes, bathed in them, listening without always realizing it. And somewhere among them, a few ancient photons from a black hole billions of years old find their way to us, bringing with them the soundless memory of power beyond comprehension. The sea of the cosmos is wide, but it is not empty. It carries voices that began before Earth existed and will continue long after it's gone. To study TON 618 is to listen closely to one of the loudest among them, a deep resonance that vibrates through everything, subtle yet eternal, reminding us that even the darkest places in the universe are full of light, and that the silence of space is only an illusion. When astronomers decided to measure TON 618, they were not simply weighing an object. They were trying to measure something that exists beyond ordinary comprehension. It is easy to talk about mass and distance, as though they are simple quantities, but when those numbers grow to cosmic proportions, the act of measuring becomes a kind of art, a mixture of observation, mathematics, and patience stretched to its limit. TON 618, being one of the farthest and largest black holes ever observed, forces science to reach into the near impossible. Its mass is not something anyone could ever place on a scale, nor its distance something anyone could travel to confirm. everything we know about it comes from indirect evidence, carefully interpreted through light that began its journey billions of years ago. When light travels such vast distances, it carries the imprint of its origin like a fingerprint. The brightness, the colour, the wavelength shifts. All of them contain clues. For an object like TON 618, astronomers rely on this light to reconstruct properties that cannot be observed directly. They measure the intensity of its radiation across different wavelengths, from visible to ultraviolet to X-rays, and then compare those readings to models of how matter behaves near supermassive black holes. By matching what's observed with what's predicted, they infer the mass, size, and energy output. It's like trying to describe an entire city after seeing the reflection of its lights in a distant lake. The reflection doesn't show the buildings or the streets, but it reveals the pattern of their existence. The most basic measurement begins with brightness. The quasar around TON 618 shines with an apparent magnitude far too faint for the human eye to see, but bright enough for sensitive instruments to detect. Once brightness is known, astronomers can calculate luminosity, the total amount of energy emitted by the source. That, combined with the estimated efficiency of accretion, gives an approximation of how much matter must be falling in per second. From there, the Eddington limit, the balance between radiation pressure and gravitational pull, provides a way to estimate the mass of the black hole powering it. It's not a single observation, but a chain of reasoning, each step based on well-tested physics, each dependent on precise measurements of light. The numbers that emerge from those calculations are staggering. TON 618's luminosity is estimated to be around 100 trillion times that of the Sun. To sustain that brightness without tearing itself apart, the central black hole must have a mass of roughly 66 billion suns. That figure is not guessed but derived from equations that connect gravity, motion, and energy. It has uncertainties, of course. Every cosmic measurement does, but even the lowest estimates keep TON 618 among the most massive black holes known. The accuracy lies not in the absolute number, but in the consistency of evidence across different wavelengths and methods. One of the key techniques used to verify these estimates is called reverberation mapping. It relies on the fact that light emitted from the inner parts of an accretion disk changes slightly over time. Those variations in brightness cause delayed responses in surrounding gas clouds, which absorb and re-emit the radiation. By measuring the delay between the original light and the echo, astronomers can estimate the size of the emission region. The longer the delay, the larger the system. With TON 618, these delays are immense, consistent with a structure that spans light years. From that scale, and from the velocity of the gas deduced through Doppler shifts in spectral lines, the mass can be inferred with reasonable precision. Spectral analysis provides another window into the measurement process. The light from TON 618 contains broad emission lines, smeared signatures of hydrogen and other elements moving at high velocities near the black hole. The width of these lines corresponds to the speed of the gas, while their position reveals redshift. The faster the gas moves, the broader the line. For TON 618, those lines are extraordinarily wide, indicating velocities approaching several percent of the speed of light. Only an enormous gravitational source could maintain such speeds without flinging the gas into space. By comparing the width of these lines to models of orbital motion around a black hole, astronomers derive the gravitational potential and, from that, the mass. Distance, too, is a challenge. When we say TON 618 is 10.4 billion light-years away, we mean that the light we see left it 10.4 billion years ago. Not that it currently sits that far from us in a static universe. The space between us and it has stretched since then. The number represents look-back time, how long the light has been travelling, not necessarily the present distance in today's expanding cosmos. To calculate that, astronomers use the redshift value of 2.2 Guanyin, plugging it into cosmological models that include the universe's rate of expansion described by the Hubble constant. The result is a comoving distance, a concept that accounts for cosmic growth. Even this is an approximation, refined as our understanding of cosmic expansion improves. What makes TON 618 fascinating is that every measurement of it, from luminosity to redshift, tests the limits of our instruments. The signal is faint, distorted, and stretched by time. Extracting data requires removing interference from nearer galaxies, correcting for atmospheric distortion, and calibrating against known reference sources. Observing such an object is a feat of both technology and persistence. Some of the data used to define TON 618 comes from surveys that combine decades of observation, piecing together fragments of signal collected from multiple telescopes around the world. It's not a single image, but a mosaic of measurements stitched together across years. Even then, uncertainty remains part of the process. Astronomers often work in ranges, not absolutes. The mass of TON 618 might be 60 billion suns, or 70, or perhaps slightly less, depending on which method is applied. Each measurement carries assumptions about geometry, efficiency, and radiation. But the consistency across independent observations gives confidence that the result is not an illusion. Whether it's 60 or 70 billion, the conclusion is the same. TON 618 sits among the giants, far beyond any known black hole in the local universe. The effort to measure something so distant raises deeper questions about what measurement really means in astronomy. We cannot physically interact with the things we study. We can only interpret their light. Every piece of data is an act of translation, from photon to voltage, from signal to spectrum, from spectrum to meaning. In that sense, measuring the unmeasurable is not about precision alone, but about trust in the consistency of nature. The same physical laws that describe gravity near Earth apply equally to a black hole 10 billion light-years away. That universality allows us to extend our reach far beyond direct experience. Still, the act of measurement always carries a margin of humility. Astronomers know that each number they publish might be revised as new instruments improve. The Hubble Space Telescope transformed our understanding of cosmic distances. The James Webb Space Telescope is now refining them further, revealing details invisible before. Future observatories will likely adjust TON 618's estimated mass again, perhaps upward, perhaps downward, but never erasing the fundamental truth of its enormity. Each refinement is another layer of understanding, another adjustment in the long conversation between evidence and interpretation. The tools that make this possible are as remarkable as the discoveries themselves. Modern spectrographs can detect differences in wavelength smaller than a fraction of a nanometer. Detectors cooled to near absolute zero minimize noise from heat. Telescopes synchronized across continents use interferometry to achieve resolution sharper than any single mirror could provide. Data is processed through supercomputers capable of sifting through trillions of measurements to isolate meaningful patterns. All of this effort, all of this precision, is aimed at deciphering signals that, to the naked eye, would appear as nothing more than the faintest point of light. It's not just the technology that makes such measurements possible, but the consistency of the cosmos. Light behaves the same way everywhere. Atoms emit and absorb specific wavelengths regardless of distance or time. Hydrogen in a distant quasar leaves the same spectral lines as hydrogen in a laboratory on Earth. That reliability turns the universe into a kind of vast measuring instrument. Each photon becomes a unit of information, a record of the conditions it experienced. TON 618's light, though ancient, still follows the same rules. That constancy is what allows us to bridge the gap between here and there, now and then. In a sense, the act of measuring TON 618 is also an act of time travel. The photons arriving at our detectors carry the imprint of a universe that no longer exists. By interpreting them, we recreate a snapshot of the cosmos as it was more than 10 billion years ago. The black hole we study may have changed, but the data we receive preserves its ancient state. Each measurement is a conversation with history, a dialogue across billions of years conducted in the language of light. Even though the black hole's true nature remains hidden, the measurements we can make reveal its scale in astonishing clarity. The mass of 66 billion suns is not just a number. It's a gravitational influence so immense that it could hold entire galaxies within its pull. The energy radiating from its accretion disk is enough to outshine thousands of Milky Ways. The fact that we can quantify such things from a distance greater than imagination speaks to how far science has stretched its reach. It shows that even the most distant and powerful objects can be brought into focus through patience and method. But measuring the unmeasurable is not only about the data, it's also about interpretation, about understanding what those numbers mean in context. For example, the brightness of TON 618 implies that it is accreting matter near the theoretical limit, but not necessarily exceeding it. That balance tells us about the efficiency of its growth and the environment of its host galaxy. The shape of its emission lines reveals the orientation of its accretion disk relative to us. Even small asymmetries in those lines can suggest whether we are viewing it face-on or at an angle. Every detail contributes to the larger picture, each one a thread in the fabric of understanding. There's something profoundly human about this process. Faced with a universe so vast that its scale defies imagination, we find ways to measure it with numbers small enough to fit on a page. We take light that's travelled billions of years and translate it into data points. We fit equations to phenomena that no one will ever witness directly. And somehow, through that combination of curiosity and precision, we come to know things that should be unknowable. TON 618 is not just an object of study, it's a symbol of that reach, of our ability to measure, model, and make sense of what lies beyond sight. The uncertainties don't diminish the achievement, they define it. Science thrives on refining what it knows. Every estimate is a step toward clarity, every revision an improvement. The fact that we can discuss TON 618's mass with even approximate confidence is itself extraordinary. The margin of error might be vast, but the conclusion remains unshakable. This is one of the largest black holes ever found, a structure whose existence challenges our understanding of cosmic evolution. As our instruments continue to improve, we may find more like it, perhaps larger still. Each discovery will add another point on the map of what's possible, another data set for comparison, and with every new measurement, our models of galaxy formation and black hole growth will sharpen. The process never ends because the universe is always deeper than our understanding. Measuring the unmeasurable is not about reaching an endpoint, but about extending the boundary of what can be known. In that sense, every photon from TON 618 is a teacher. Each one has travelled across the expanding fabric of space, carrying information about gravity, temperature, and motion. By catching those photons, by measuring their energy and direction, we participate in the act of decoding the universe. It's a slow, meticulous conversation, conducted in silence, yet filled with meaning. And even though the object we study is invisible, the data it provides shines brightly enough to illuminate the edges of what science can grasp. And so, the act continues, one signal at a time, one equation at a time, one refinement after another. The numbers we derive may never feel intuitive, but they form a bridge between thought and the cosmos, between curiosity and the unknown. TON 618, the unseeable giant, remains our most distant mirror, reflecting not just the power of gravity but the human urge to understand what lies beyond every horizon we can measure. When we look at the universe through telescopes, what we see first are galaxies, vast islands of stars scattered across the cosmic ocean. Their shapes vary, spirals with sweeping arms, ellipses smooth and diffuse, irregular forms twisted by collisions. To the eye they seem calm, suspended in the emptiness, each shining as a single coherent system. But inside each one, deep in the centre, there is motion. Hidden behind the clouds of stars and dust lies something that controls the entire structure, a supermassive black hole. These silent centres are the quiet architects of galaxies, shaping everything around them without ever revealing themselves directly. For a long time, astronomers thought black holes were rare, perhaps the result of unusual accidents in stellar evolution. That changed when technology improved enough to see the influence they exerted. The evidence emerged slowly but decisively. Stars near galactic centres move too quickly to be explained by visible matter alone. Clouds of gas orbited invisible masses with astonishing speed. Light from background stars bent as if warped by unseen gravity. The conclusion became inescapable. Nearly every large galaxy harbours a supermassive black hole at its core. Some are active, blazing as quasars like TON 6 and 18. Others are quiet, dormant and nearly invisible, but all of them are there, anchoring their galaxies in place. It's easy to imagine black holes as destructive, but in cosmic terms they are organisers. Their gravity pulls gas and dust toward the centre, encouraging stars to form in dense regions. They stabilise the orbits of stars in their neighbourhoods. Their radiation and jets regulate the flow of matter across interstellar space, preventing galaxies from growing too quickly or collapsing under their own gravity. In this way, black holes act as both engines and governors of galactic evolution. They are destructive locally but constructive globally. TON 618, with its colossal mass, represents this process magnified to its limits. It's not just a feature of its galaxy, it defines it. The gravitational influence of a black hole at large extends far beyond its immediate surroundings. Stars many light years away feel its pull. The orbits of gas clouds, the shape of spiral arms, and even the overall stability of the galaxy depend, at least in part, on that invisible presence. It acts as a gravitational anchor, giving structure to the whole. Without such a centre, galaxies might disperse over time, their stars drifting apart into the void. At first, this idea seemed counterintuitive. How could something that consumes light and matter also build structure? The answer lies in feedback, the cycle of energy and regulation that links the black hole to its host. When a black hole like TON 618 feeds, it releases enormous amounts of radiation. That energy heats surrounding gas, sometimes driving it away. In doing so, it controls the pace of star formation. Too much gas condensed into stars too quickly would exhaust a galaxy's resources. Too little would leave it dim and lifeless. The feedback from the central black hole maintains a balance, ensuring that galaxies evolve steadily rather than burning out early. This relationship is reflected in one of the most consistent patterns in astrophysics: the correlation between the mass of a galaxy's bulge, the dense central region, and the mass of its black hole. It's known as the M-sigma relation. The bigger the bulge, the bigger the black hole, and vice versa. The fact that this connection holds across millions of galaxies suggests that their growth is not independent. The black hole and the galaxy grow together, each influencing the other through gravity and energy. In that sense, black holes are not passengers in galactic evolution. They are architects working quietly behind the scenes. Our own Milky Way follows this pattern. At its centre lies Sagittarius A, a supermassive black hole with about 4 million solar masses. It's relatively calm today, but the region around it bears scars of past activity. Gas clouds heated to extreme temperatures, radio emissions from older jets, and star clusters that likely formed from compressed material long ago. These traces suggest that Sagittarius A was once more active, perhaps even quasar-like, billions of years ago. TON 618, seen as it was in the distant past, may represent that earlier phase on a far grander scale. Looking at it is like looking at what our galaxy might have been in its youth. The presence of black holes also helps explain why galaxies take the shapes they do. In spiral galaxies like the Milky Way, the central mass stabilizes the rotating disk of stars and gas. In elliptical galaxies which form through mergers, the resulting black hole merges too, producing bursts of radiation that smooth out irregularities. Even in dwarf galaxies, the smallest systems, Recent studies have found evidence of black holes scaling proportionally with their total mass. From the tiniest galaxies to the largest clusters, this pattern repeats. It's as if the universe insists on building structure around these dense cores, using them as blueprints for balance. One way to think of a black hole's role in a galaxy is to imagine a conductor in an orchestra. The conductor doesn't play the instruments, but sets the tempo, ensures harmony, and keeps everything moving together. Without that guidance, the result would be chaos. In the same way, black holes, though invisible, set the rhythm of their galaxies. Their energy output, their gravitational influence, and their timing all contribute to the cosmic balance. TON 618, operating at its extreme scale, is a conductor leading an orchestra of billions of stars across a span of space larger than any metaphor can quite capture. It's important to remember, though, that this process happens slowly. The timescales involved are beyond human experience. A black hole's influence unfolds over millions or billions of years. The stars orbiting it may take entire epochs to complete a single revolution. The feedback cycles that shape galaxies stretch across cosmic ages. When we observe TON 618's light, we're seeing only one frame in that vast movie. Its current state, the brightness, the feeding, the radiation, is just a brief phase in a story that began long before and will continue long after. For scientists, the challenge is to connect these snapshots across time. By observing galaxies at different distances, and therefore at different ages, astronomers can reconstruct how the relationship between black holes and galaxies evolved. Younger galaxies show more active quasars, while older ones show quieter cores. This trend supports the idea that black holes feed most vigorously early in a galaxy's life, and then settle down. TON 618, being one of the brightest and oldest quasars known, fits perfectly into that pattern, a glimpse of an era when the universe was still building itself, when gravity and gas were in constant competition. The quiet architects don't stop working when the feeding ends. Even a dormant black hole continues to shape its surroundings. Its gravity keeps stars bound in stable orbits. Its history leaves imprints in the structure of the galaxy, and its presence influences how future generations of stars will form. Over time, as galaxies merge, their central black holes merge as well, combining their masses and energy. These cosmic unions send gravitational waves rippling through space-time, waves that instruments like LISA, a planned space-based observatory, will one day detect. When that happens, we'll be listening directly to the heartbeat of galactic architecture itself. The influence of black holes extends even further. They affect not only their host galaxies, but also the space between galaxies. The jets and winds from quasars inject energy into the intergalactic medium, enriching it with heavy elements and stirring it with turbulence. This, in turn, influences how new galaxies form in nearby regions. TON 618's jets, if mapped in full, could stretch millions of light-years, depositing material and energy far beyond its home galaxy. In this way, it participates in the larger ecosystem of the universe, helping to shape the cosmic web, the network of filaments and voids that defines the large-scale structure of everything. It's humbling to realize that all of this, the shape of galaxies, the rhythm of star formation, the flow of energy across space, depends on processes that began with the simplest rule: gravity pulls. There's no conscious design behind it, no intention. Yet from that single force, complexity emerges. Black holes, by their nature, represent the endpoint of collapse, but that same collapse drives creation elsewhere. Without them, the universe would be flatter, duller, less structured. The contrast they introduce, between emptiness and density, darkness and light, gives the cosmos its form. When scientists study TON 618, they're not just learning about a single object, but about this entire process of cosmic construction. Its enormous mass and energy output are extreme versions of what happens everywhere on smaller scales. By understanding how TON 618 formed and evolved, We learn how galaxies like our own came to be. Every observation adds another layer to the picture of how gravity and energy balance each other over time. It's a reminder that even the most remote and violent parts of the universe are connected to our own origins. The term quiet architects fits because black holes don't announce their work. Their influence is invisible, indirect and slow. Yet without them, the structures we see in the night sky would not exist. They give galaxies their centres, their cohesion, and in many cases their brilliance. Even when they fade from view, their gravitational signature remains, shaping the motion of stars for billions of years. In that way, they are both creators and witnesses, building the framework of the universe while remaining hidden within it. Our understanding of them continues to deepen. New simulations powered by supercomputers show how galaxies and black holes co-evolve. They reveal feedback cycles where jets and radiation sculpt vast regions of gas, and where the timing of those events determines a galaxy's fate. The more we model these systems, the more we realize that the line between destruction and creation is thin, and that the universe thrives precisely in that tension. TON 618, frozen in our view as it was 10 billion years ago, sits at the extreme edge of that balance. Its existence proves that the early universe could produce giants capable of shaping everything around them. Perhaps one day, future generations will look deeper into the cosmos and find black holes even larger, galaxies even more massive, and patterns even clearer. But the principle will remain the same. Every structure, every star, every cluster will trace its ancestry back to the same process. Gravity gathering matter around invisible centres, allowing the universe to organise itself. TON 618 just happens to be one of the clearest and most powerful examples of that principle, the ultimate architect working quietly at the edge of time. And as we continue to study it, measuring its echoes, analysing its light and comparing it to others, we're not just mapping a distant galaxy. We're tracing the design of the universe itself, one that has no drafts or revisions, only endless iteration, each galaxy a version of the same plan, each black hole a signature on that cosmic blueprint. The galaxies we see today, calm and mature, owe their form to those early active epochs, when black holes like TON 618 ruled the centres of their worlds. Even though their work is invisible now, its results are everywhere. In the spirals of stars across the sky, in the balance of energy that allows planets to exist, and in the quiet persistence of gravity shaping everything from atoms to clusters of galaxies. So when we look up at the stars, what we see is the architecture left behind, the product of forces that built and balanced the universe long before we arrived. And at the heart of it all, silent and unseen, the black holes remain. The quiet architects of galaxies, the steady anchors of a cosmos still under construction. When we observe TON 618, we are not seeing it as it is, but as it was. Its light began the journey toward us more than 10 billion years ago, when the universe was young and restless, still finding its shape. Every photon that reaches our telescopes today has travelled through time, crossing epochs of change, passing through the shifting fabric of space that expanded and stretched along the way. In that sense, looking at TON 618 is not just an act of seeing across distance. It's an act of time travel. The light we receive carries with it a memory of a universe that no longer exists, a universe still in the process of becoming. That idea can be difficult to grasp because our daily lives unfold in a world where time feels linear and constant. We wake, we move through the day, and we sleep. We measure hours and years as though they flow evenly in one direction. But in the cosmos, time and distance are connected. The farther away an object lies, the older the light we see from it. When we look across space, we're looking down a corridor of history. The night sky above us is not a map of the present, but a mosaic of different moments, each star and galaxy representing a different point in time. Some of the light reaching us tonight began its journey before life appeared on Earth, some before Earth itself formed. TON 618 is among the oldest of these messengers. When its light first set out, the universe was only about a quarter of its current age. The first galaxies were forming, drawn together by gravity from immense clouds of hydrogen and helium. The cosmic web, that vast structure of filaments and voids that connects everything, was just starting to take shape. Quasars like TON 618 burned brightly in that early era, marking the locations of massive black holes at the centres of young galaxies. Their light became signposts across time, guiding astronomers today to understand what the universe looked like when it was still in its formative stages. To trace that journey of light is to retrace the history of everything. The photons that left TON 618 travelled through expanding space, their wavelengths stretched by the motion of the universe itself. They passed through intergalactic clouds, through clusters of galaxies, and through regions of near absolute emptiness. Some were absorbed and re-emitted, some scattered, some delayed by gravitational lensing as they skirted massive objects along the way. Yet enough of them arrived, intact and coherent, to tell their story. Each photon carries within it a fragment of history, the energy of an atom near the edge of a black hole, released before our solar system existed. When astronomers measure the redshift of TON 618, they're not just calculating distance, they're decoding time. A redshift of 2.219 means that the wavelength of its light has been stretched by more than 3 times due to cosmic expansion. That stretching corresponds to a look-back time of over 10 billion years. The numbers may seem abstract, but they place TON 618's light in a specific epoch, a time when galaxies were smaller, denser, and more chaotic, when the first generations of stars were still forging heavy elements. The universe then was a different place entirely, filled with radiation, turbulence, and motion. In that early era, the cosmic background temperature was higher. The galaxies we now see as distinct islands were closer together, interacting frequently. Collisions were common, mergers constant. These interactions triggered waves of star formation, fueling the growth of central black holes. TON 618's size suggests that it was born in one of those early, turbulent regions, a place rich in gas, where gravity had ample material to work with. Its brilliance marks it as one of the dominant quasars of its time, a lighthouse in a universe still glowing from its own creation. If we could somehow travel to that era, what we'd see would be both familiar and alien. The laws of physics would be the same, but the view would be unlike anything near our modern Milky Way. The night sky of that time, seen from a nearby galaxy, would be filled with active quasars. Everywhere young stars would burn hot and blue. The darkness between galaxies would be thinner, more luminous with scattered light. Space itself would appear slightly warmer, bathed in the afterglow of the Big Bang that had not yet faded to the cold whisper we measure today. The light from TON 618 bridges that gap between then and now, serving as a time capsule of that epoch. It tells us that massive black holes existed earlier than anyone once thought possible. It shows that the universe reached levels of complexity, galaxies, stars, and organised structure, much sooner than our models predicted. Every observation of TON 618 challenges and refines those models, forcing us to rethink how quickly gravity can assemble such immense objects from primordial gas. This process of looking back is not limited to TON 618. Every astronomical observation is a form of archaeology, uncovering layers of cosmic history through light. When we observe a star 1,000 light-years away, we're seeing it as it was 1,000 years ago. When we study the Andromeda Galaxy, we're looking at light 2 million years old. With TON 618, we stretch that timeline to cosmic extremes, 10 billion years into the past, almost 3/4 of the way to the beginning of time itself. The scale defies intuition, but the principle is the same. Light travels at a finite speed, and in doing so, it records the passage of time in its motion. What's remarkable about this cosmic time travel is that it requires no movement on our part. We stay still, and the light comes to us. Our telescopes act as windows, opening not only into space but into history. The further we peer, the deeper into the past we go. The James Webb Space Telescope, for example, has extended that reach even farther, capturing the light of galaxies formed less than 500 million years after the Big Bang. TON 618 stands somewhere in between, distant enough to be ancient, close enough to be studied in detail. It sits at a point in the timeline where the universe was already full of stars but still wild and unstable, caught between creation and order. The photons that left it have aged along the way, though light itself does not experience time. For those photons, the journey from TON 618 to Earth was instantaneous. From our perspective, it spanned most of cosmic history. This contrast, timelessness from one viewpoint, deep time from another, captures one of the most profound truths of relativity. Time is not a universal river flowing the same for all things. It bends, it stretches, it depends on motion and gravity. TON 618 teaches that lesson with every beam of light it sends us, each one a bridge between two vastly different moments that coexist in a single observation. The idea that we can look into the past simply by looking up changes how we think about our place in the cosmos. It means that everything we see is part of an ongoing story, not static, not separate, but connected across time. The galaxies we observe are at various stages of life, some just forming, others already dying. TON 618's light is from a time when life on Earth was still billions of years away. Yet that light now touches our instruments, our data, and our thoughts. It binds the ancient and the modern, the distant and the immediate in a single continuum. In the process of studying that light, we've also learned about the large-scale structure of the universe. The path from TON 618 to us is not a straight line through emptiness. It passes through a cosmic web of filaments made of dark matter and gas. These filaments connect galaxies like threads in an immense tapestry. The light from distant quasars helps trace that structure, revealing the invisible distribution of matter across space. As photons pass through these regions, they are slightly absorbed and scattered, leaving subtle fingerprints in their spectrum. By studying those patterns, scientists can map the otherwise invisible scaffolding that holds the universe together. That's how TON 618 contributes not only to our understanding of black holes, but also to our understanding of the universe itself. Its light acts as a probe, sampling the intervening material between galaxies. From it, we can infer the density of hydrogen, the temperature of intergalactic gas, and even the influence of dark matter on cosmic expansion. Every photon that arrives carries more than one story. It tells us about the black hole that emitted it, and the universe it passed through. What makes this perspective so powerful is that it connects time and structure in a single observation. TON 618 is not just a point in the sky. It's a marker on the timeline of existence. By comparing it with quasars closer to us, astronomers can see how the universe evolved, how galaxies changed shape, how star formation rates shifted, how the intergalactic medium cooled. It's like watching the growth of a living organism through snapshots taken over eons. Each quasar becomes a frame in the film of cosmic history, each one showing a slightly different stage of the same story. This ability to look back has another consequence. It shows us that nothing lasts forever. TON 618's brilliance, though immense, is temporary. The matter fueling it will eventually run out. The light that now travels toward us will fade. In time, its galaxy will quiet, its energy will settle, and the black hole will remain, invisible but still massive. Even its radiation, after billions of years more, will dissipate into the background. But that doesn't diminish its significance. The traces it leaves, in the structure of its galaxy, in the light that reaches us, in the data we gather, become part of the permanent record of the universe. When you think about that record, it's astonishing how much of it exists purely in light. No physical relics connect us to TON 618, no debris or matter that we can touch. Everything we know comes from waves of energy that have crossed the universe, Yet those waves are enough to reconstruct entire histories. The idea that photons, massless particles moving through expanding space, can carry information so detailed that we can measure the spin of a black hole billions of years old, that alone is a reminder of how complete the language of physics can be. In that light, TON 618 becomes more than a distant object. It becomes a witness. Its glow, ancient and unchanged, speaks to what the universe once was. It reminds us that everything we see is transient, that the vast structures of today were once chaotic and small. It shows us that creation and destruction are not opposites, but parts of a continuous process, stretching across time so immense that even the word age seems inadequate. And so, every observation of TON 618 is also an act of remembrance, a way of acknowledging that we exist in a moment shaped by countless events before us. The galaxies that gave rise to black holes like TON 618 paved the way for the universe we know. The heavy elements in our own planet were forged in stars that lived and died during those epochs. In a sense, we are made from the same history that light reveals. We are not just observers of time, but products of it, shaped by the same forces that created the things we study. Looking at TON 618, therefore, is like looking into a mirror that reflects not just distance, but ancestry. Its ancient light carries the memory of beginnings that led eventually to us. Every photon that reaches our detectors has travelled longer than life itself has existed. That continuity connects the smallest part of our world to the largest scales of the cosmos. The past, preserved in light, flows into the present through every observation, reminding us that even the most distant events still echo in the world we know. And as new instruments look deeper still, beyond TON 618 into even earlier times, we will keep travelling backward, uncovering the universe as it once was, not through imagination, but through evidence carried by light across the ages. Each discovery will take us closer to the beginning, closer to understanding how time itself unfolded, until eventually the first sparks of creation come within reach of our instruments. In that sense, TON 618 is both a destination and a milestone on that journey, a beacon guiding us through time, reminding us that every point of light in the sky is also a doorway into history, waiting patiently for us to open it. The light from TON 618 began its journey toward us during a time when the universe was still young and restless, filled with more energy and motion than any era since. It was an age of abundance and hunger, when everything was consuming everything else in the process of becoming something greater. Galaxies were forming in dense clusters, drawing gas from vast cosmic filaments. Stars were igniting at extraordinary rates. Black holes, like the one that would become TON 618, were feeding at the limits of physics. It was a universe still learning balance, growing quickly, expanding, cooling and changing, from a sea of gas into a structured cosmos. At that point in cosmic history, roughly 3 billion years after the Big Bang, the universe was about 1/5 of its current age. The temperature of the cosmic background radiation had dropped enough for galaxies to form clearly, but the space between them was still warmer and thicker with gas. The first heavy elements had begun to appear, created in the cores of the earlier stars and distributed by supernova explosions. These new ingredients, carbon, oxygen, silicon, iron, changed everything. They made it possible for more complex chemistry, for planets to eventually form and for black holes to grow faster. The young universe was far from quiet. It was noisy with radiation, crowded with collisions and filled with the glow of newly forming galaxies. The cosmic web, the great network of filaments connecting everything, was bright with energy, gas flowing like rivers into gravitational wells. In those wells, matter condensed, stars formed, and the first galaxies took shape. The balance between gravity pulling in and pressure pushing out determined where these galaxies would form and how massive they would become. TON 618's host galaxy likely occupied one of the densest intersections in that web, where gas streams converged, fueling rapid growth. It's easy to imagine the early universe as empty and dark, but it was the opposite. It was crowded, luminous, and active. Black holes were not the silent giants we think of today. They were brilliant, consuming matter at incredible rates, releasing torrents of radiation that lit up the darkness. These early quasars were the first great beacons of light after the cosmic dawn, the period when the first stars rionized the hydrogen that had filled space since the Big Bang. Before that, the universe had been opaque, filled with neutral hydrogen that absorbed light. But as stars and quasars formed, their radiation stripped electrons from those atoms, clearing the fog and making the universe transparent. TON 618's ancestors helped perform that transformation, turning the cosmos from shadow into light. The hunger of that young universe wasn't chaotic. It followed patterns that physics dictates. Gas flowed along gravitational gradients, collecting in the deepest wells where dark matter had already gathered. Dark matter, invisible yet dominant, provided the scaffolding for structure. Without it, the ordinary matter we see, the stars, the gas, the galaxies, would never have had time to clump together. Where dark matter density was high, galaxies grew quickly. Where it was sparse, the universe remained thin and quiet. TON 618's galaxy formed in one of those dense regions, a place where gravity reigned supreme and the available gas was plentiful. In that environment, growth was rapid. Stars formed in bursts, their lifespans brief but productive. Massive stars lived fast and died young, exploding as supernovae and leaving behind black holes that merged into larger ones. Each generation enriched the surrounding gas with heavier elements, making the next generation of stars more complex. The process built upward, layer by layer, from hydrogen and helium to the diversity of matter we see now. In only a few billion years, the universe went from uniform to structured, from featureless to filled with galaxies like the one that housed TON 618. The black holes of that era grew alongside their galaxies, feeding on the gas funneled toward their centres. The more they consumed, the more they influenced their surroundings. Radiation from the accretion disks heated nearby gas, sometimes preventing new stars from forming, sometimes triggering them by compressing clouds further out. It was a delicate interplay, one that set the pace for cosmic evolution. TON 618 represents the most extreme outcome of that process, a black hole that managed to feed more efficiently and grow faster than almost any other known. How it did so remains an open question. According to current models, black holes form from the remnants of massive stars, typically a few dozen solar masses. To reach tens of billions of solar masses in just a few billion years, TON 618's ancestor must have had a head start. Some theories suggest that in the early universe conditions were ripe for direct collapse. Massive clouds of primordial gas collapsing straight into black holes without forming stars first. These seed black holes could start with masses of hundreds of thousands or even millions of suns. From there, constant feeding and mergers could produce giants like TON 618. Other theories propose that these early black holes grew through super-Eddington accretion, feeding faster than the theoretical limit imposed by radiation pressure. In such cases, matter might have flowed inward so quickly that light couldn't push it away fast enough. The accretion disks would have been thicker, denser, and more chaotic than those of modern quasars. It's a process that challenges our understanding of physics, but may explain how black holes reach such sizes so early. TON 618, being as luminous as it is, provides evidence that such extreme feeding was possible. The hunger of the early universe extended beyond black holes. Galaxies themselves were consuming each other. Mergers were frequent, driven by gravity and proximity. When two galaxies collided, their stars rarely hit directly. The distances between them were too great, but their gas and dust mixed violently. Shockwaves triggered new rounds of star formation. Their central black holes spiraled toward each other, eventually merging in events so powerful that they sent gravitational waves rippling through space-time. These collisions were both destructive and creative, producing larger galaxies and more massive black holes in the process. It's strange to think that what now appears as the serene order of the cosmos began in such chaos. But that chaos was productive. The turbulence of the early universe set the foundation for the calm structure we see today. Every quiet galaxy, every stable orbit, every planet owes its existence to that earlier age of intensity. The hunger of the cosmos was not wasteful. It was the mechanism through which complexity emerged. Even as Ton 618's light began its long journey, the universe was already changing. The rate of star formation peaked around that time and has been declining ever since. The universe was using up its easily accessible fuel. The galaxies that formed later would be less active, their stars more stable, their black holes quieter. The violent youth of the cosmos gave way to maturity. Ton 618 stands as a relic of that earlier era, a fossil of the universe's appetite preserved in light. The scale of that appetite is difficult to convey. During its active phase, Ton 618 may have consumed thousands of Earth's worth of matter every year. The energy it released exceeded the combined output of countless galaxies. That radiation shaped not just its immediate surroundings, but also the intergalactic medium. It pushed gas outward, altered the temperature of nearby regions, and even slowed the growth of smaller galaxies around it. The influence of one feeding black hole could stretch for millions of light years. The universe then was dense enough that such interactions were common. The distances between galaxies were smaller, meaning their effects overlapped. The result was a complex feedback network where the energy of one object affected many others. Ton 618's radiation would have echoed through that network, its light scattering and blending into the cosmic background that still fills space today. Somewhere in that faint glow is the residue of its ancient activity, mixed with the light of countless others that once burned just as brightly. Understanding that era requires more than observation. It requires simulation. Astronomers use supercomputers to recreate the early universe, modelling how matter flowed, how galaxies formed, and how black holes grew. These simulations, while limited by computational power, consistently show that early quasars played a key role in shaping cosmic evolution. They heated and ionized vast regions of space, influenced the distribution of gas, and set the pace for future star formation. Without them, the universe would look very different. Ton 618, by existing, confirms that the conditions necessary for such growth were not only possible, but common enough to leave lasting effects. When we imagine that young, hungry universe, it's easy to think of it as violent or chaotic, but it was also efficient. Every burst of energy, every collision, every feeding phase contributed to the balance that allowed the cosmos to mature. The energy released by quasars like Ton 618 was not wasted. It spread evenly, enriching and shaping the regions around them. Over time, that energy cooled, galaxies settled and stars stabilized, but the memory of that early hunger remains encoded in the large-scale structure of space. Even today, astronomers can trace that legacy. The heavy elements we find in intergalactic gas, oxygen, carbon, iron, were forged in those early stars and spread by their explosions. The black holes at the centres of modern galaxies are the descendants of those early giants. The background radiation we detect with radio telescopes carries the imprint of their heating. Every observation we make points back to that same period, the time when the universe was young, hot, and full of appetite. And it's not just a story of scale, it's a story of transformation. The matter that once swirled in the disks of early quasars has since become part of new galaxies, new stars, and new worlds. The hydrogen that fell into Ton 618's accretion disk may have come from gas clouds that once drifted between galaxies, and the atoms that didn't fall in may have gone on to form other systems entirely. Even destruction feeds creation in the long run. As the universe aged, expansion stretched space and cooled its contents. Galaxies drifted apart, the frequency of collisions decreased, and the great cosmic hunger began to quiet. Ton 618's feeding, once a blazing beacon, likely subsided long ago. The fuel ran out, the accretion slowed, and the glow faded. Yet the black hole remains, its mass unchanged, its gravity undiminished, silently holding its galaxy together. What was once the heart of a raging storm is now a monument to what the universe used to be. Proof that even chaos can lead to order when given enough time. The young universe was hungry because it was growing. It consumed to create, destroyed to build, and radiated to balance itself. In that balance, the first great structures emerged, and through that process, everything we see, from the faint light of distant galaxies to the atoms in our own bodies, found its place in the ongoing transformation of matter and energy. Ton 618, frozen in light from that ancient era, is a window into that hunger, not just the hunger of gravity or matter, but of the universe itself to become more complex, more structured, and more alive with possibility. It reminds us that the calm we see today was born from intensity, that the peace of the modern cosmos rests on the foundation laid by an age of fire, motion, and insatiable growth. And somewhere, in the depths of that ancient light, the echoes of that hunger still travel, still reaching across the endless distance, carrying with them the story of a universe that once fed on itself to learn how to shine. As far as we can see, the universe is vast beyond comprehension. Yet even that distance, measured in billions of light years and filled with countless galaxies, is only part of a much larger reality. The light that reaches us, no matter how ancient, carries information only from within the observable universe, the region from which light has had time to travel since the beginning of time. Beyond that lies a boundary we cannot see, not because it doesn't exist, but because the light from there will never reach us. That limit, imposed by the finite speed of light and the expansion of space, is one of the most humbling frontiers of knowledge. It's what astronomers mean when they talk about the edge of what we know. Objects like Ton 618 sit near that frontier, on the far edge of our cosmic horizon, their light arriving from an era not long after the birth of galaxies themselves. When we observe them, we're reaching as far into space and as far into the past as our instruments allow. Yet even as we measure and model, there's always a point beyond which data turns into inference, and inference turns into speculation. The universe is not only vast, it's patient. It reveals itself slowly, in fragments of light, always keeping part of its story hidden behind the horizon of visibility. The human desire to understand what lies beyond that edge has driven science since the beginning. Every time our telescopes improve, the boundary shifts. When radio astronomy began, it extended our vision into wavelengths the eye could never see. When space telescopes were launched, they escaped the distortions of Earth's atmosphere and revealed galaxies billions of light years away. Now, with the next generation of observatories, we're detecting light from the earlier stars just hundreds of millions of years after the Big Bang. And yet, the further we look, the more questions emerge, questions that sit quietly at the limits of our equations. One of those questions concerns the true nature of black holes themselves. Ton 618, immense as it is, challenges what we think is possible. According to most models, black holes in the early universe shouldn't have had time to grow that large. The standard sequence, star death, collapse, accretion, merger, requires more time than the universe had at that point. The existence of Ton 618 suggests that something in our understanding of formation, accretion, or time itself might be incomplete. Perhaps there were mechanisms of rapid growth we haven't yet observed, or perhaps our assumptions about the early conditions of space need revision. The evidence fits within physics as we know it, but just barely. That uncertainty marks the edge of knowledge, the place where evidence ends and possibility begins. In science, those edges aren't failures, they're signposts. They show where our models reach their limits and where new ideas must take root. The history of astronomy is a sequence of such frontiers. There was a time when stars themselves were thought eternal, when galaxies were not yet known to exist, when the idea of the universe having a beginning was controversial. Each of those boundaries eventually fell, replaced by deeper questions. TON 6-18 and others like it stand as the current boundary, reminders that even with all we've learned, the cosmos still holds secrets beyond our reach. The challenge of studying such objects goes beyond technology. It forces us to reconsider the language we use to describe the universe. Terms like space, time, and mass are human inventions, tools that work well within familiar scales but begin to blur at extremes. Near a black hole, space folds and time stretches. The equations that describe those distortions are precise, but their meaning becomes difficult to picture. When we talk about something with a mass of 66 billion suns compressed into a region smaller than our solar system, words start to lose their grip. At that point, we're not just measuring the universe, we're testing the boundaries of imagination. It's worth remembering that every breakthrough in science has come from confronting those boundaries. When Newton described gravity, he gave the first framework for predicting motion across the cosmos. Centuries later, Einstein expanded that framework, showing that gravity wasn't a force pulling through space, but the curvature of space itself. Now physicists are searching for a theory that unites gravity with quantum mechanics, a theory that can describe both the vast and the small in one consistent picture. Somewhere inside TON 6-18, where space-time curves to its limits, that theory would find its ultimate test. At present, the two great pillars of physics, general relativity and quantum theory, coexist uneasily. Each works perfectly within its domain, but together they produce contradictions. General relativity describes how gravity shapes the universe on large scales. Quantum theory governs the behaviour of particles on the smallest. Inside a black hole, both sets of laws apply, yet they disagree about what happens. Relativity predicts a singularity of infinite density. Quantum mechanics forbids infinities, demanding that something intervene to prevent collapse. The point where these frameworks collide is, quite literally, the edge of what we know. TON 6-18 is too far and too massive to probe directly, but it serves as a natural laboratory for these ideas. The behaviour of its accretion disk, the way it emits radiation, the structure of its magnetic fields. All these things provide indirect clues about the physics of extreme gravity. Observing them helps refine theories that might one day explain not just black holes, but the origin of space and time themselves. In that sense, studying TON 6-18 is not just about understanding one object. It's about testing the foundations of reality. The concept of the observable universe is another reminder of how knowledge has limits built into it. The cosmic horizon, the maximum distance light has travelled since the Big Bang, defines the outer edge of what we can see. Beyond it, the universe may continue indefinitely, filled with galaxies that will remain forever hidden from us because their light will never reach our position in time. It's not a wall or a boundary in space, but a limit imposed by time and expansion. The thought that most of the universe is permanently beyond our view is both humbling and oddly comforting. It means there's always more than we can know, always a vast unknown sustaining the known. Astronomers deal with that unknown by working inward. They study the observable in exquisite detail, building models that can be tested and refined. When predictions hold, confidence grows that the unseen follows the same laws. When they don't, something new must be learned. TON 6-18 pushes those tests to extremes. Its brightness, its mass, and its age stretch the parameters of every model that tries to explain it. In doing so, it keeps science honest, reminding us that theories are only temporary scaffolds around a truth too large to contain. At the edge of what we know, humility becomes a scientific tool. The willingness to admit uncertainty, to refine or even discard long-held ideas, is what allows discovery to continue. Every time astronomers point their instruments at something like TON 6-18, They're not just confirming what they expect. They're also searching for the moment when expectation breaks, when the data no longer fits. Those breaks are where progress begins. Even our methods of observation approach their limits here. The light from TON 618 is so faint, so red-shifted, that detecting it requires enormous telescopes and long exposures. Instruments must be cooled, calibrated, and shielded from interference. Computer algorithms must separate genuine signal from noise. Every measurement carries layers of uncertainty. Yet the fact that we can extract any data at all, that we can describe something 10 billion light-years away in terms of numbers and models, is an achievement that would have seemed impossible to earlier generations. It shows how far we've come and how far there still is to go. The questions that emerge at this frontier go beyond black holes. They reach into the very nature of the universe. What came before the Big Bang? Why do the laws of physics take the form they do? Is our universe the only one, or part of a larger multiverse? These questions remain speculative, but they grow naturally from the same curiosity that led us to measure TON 618. To know one extreme of reality is to wonder about all the others. The edge of what we know is not a fixed point. It moves outward with every discovery, expanding just as the universe itself does. Even the simple act of seeing, of turning light into knowledge, has philosophical weight. When we observe something as distant as TON 618, we participate in a chain that began with an atom near a black hole, emitting a photon billions of years ago. That photon travelled through space, through time, through cosmic expansion, and ended its journey in a human-made detector. It's a connection that spans nearly the entire history of the cosmos. To measure it is to bridge the gap between the beginning and the present, between the impersonal laws of physics and the awareness that can perceive them. At the limits of comprehension, science and wonder converge. The deeper we look, the more we realise that the unknown is not an absence of knowledge, but the source of it. The boundaries of understanding are what make curiosity possible. Without them, there would be nothing to explore. TON 618, enormous and unreachable, embodies that principle. It stands as a reminder that there will always be more beyond the horizon, more questions, more mysteries, more to learn. And perhaps that's the quiet truth of the universe. The edge of what we know is not a line to be crossed, but a landscape to be explored endlessly. Each discovery expands it, not by replacing mystery with certainty, but by revealing new layers of mystery beyond. The light from TON 618, travelling across billions of years, carries not just information about a distant black hole, but a reflection of our own search for understanding. It shows that knowledge is never complete, that even in a universe governed by laws, there is infinite room for curiosity. To imagine what would happen if you fell toward a TON 618 is to stretch the limits of what thought can hold. The human mind evolved to understand the world at human scales. Mountains, oceans, the curve of a planet's horizon. The reality near a supermassive black hole belongs to a different order of existence entirely. Yet imagining it is irresistible, because it allows us to test what we know about gravity, time, and motion, and to picture, however faintly, what lies beyond every horizon of experience. If you could begin the journey, you would not start in darkness. TON 618, like most active quasars, would blaze with light visible from millions of light-years away. The accretion disk around it, wider than the entire orbit of Neptune, would outshine every star in its galaxy combined. From a safe distance, it would look almost like a star itself, except that its brightness wouldn't flicker the way starlight does when seen through atmosphere. It would be steady, pure, and impossibly intense. A fixed point that pierced the dark with power far beyond any natural light source known. As you approached, that point would spread into a disk, a flat, swirling storm of gas and plasma spinning at nearly the speed of the light. The colours would depend on distance. Far from the centre, the light would glow with a soft bluish hue. Closer in, it would shift through ultraviolet, then into X-rays invisible to human eyes but deadly in their intensity. The energy near that region would be so great that matter no longer behaves as it does on Earth. Atoms would be stripped of their electrons, forming a plasma where charged particles spiral along magnetic fields, releasing radiation as they move. It's a place of pure dynamics, where motion itself becomes luminous. You wouldn't be able to approach this storm directly. The radiation would be lethal long before gravity became the dominant danger. Spacecraft shielding that can survive near a star would be instantly vaporized near Ton 6-Methane's accretion disk. The temperature of the gas there reaches hundreds of millions of degrees. But since this is a thought experiment, imagine yourself protected by something that ignores physical limits. A way to see without being destroyed, to witness without being part of the process. From that vantage point, hovering just above the accretion disk, you would see the universe distorted by gravity. Light from the far side of the disk would bend around the black hole, wrapping into a glowing ring. Every direction would lead back to the same object. Space itself would appear warped, as if the geometry of the world had been folded into a funnel. The top of the disk, the underside, and the horizon would all seem visible at once. The sense of direction would fade. Up and down would lose meaning. Only the inward pull would remain. If you began to fall, you would not feel motion at first. Gravity works by pulling on everything equally, so your body would seem weightless. You'd accelerate, but with no resistance, no sound, no reference. The only sign of change would be the increasing speed of the disk beneath you and the redshift of the universe behind you. As you descended, time itself would begin to stretch. To an outside observer, your fall would appear to slow, your motion freezing just above the event horizon. But from your own point of view, nothing would seem different. You'd continue falling normally, unaware that the rest of the universe was racing ahead. That difference in perception is one of the strangest aspects of relativity. To someone watching from a distance, you would never cross the horizon. Your image would fade, redshifted into darkness, your final light frozen just above the edge. But for you, the fall would continue smoothly. The horizon is not a physical barrier. It's a region of space-time where the flow of time and space trade places. Outside, space moves through time. Inside, time moves through space. Once crossed, every direction leads inward, and escape becomes not just impossible, but meaningless. As you approach that invisible line, the view would change again. The light from the disk would curve around you, forming a halo that stretched in all directions. The universe beyond would appear to contract into a small, bright sphere above, while below, the blackness would deepen infinitely. You'd see light circling the horizon, trapped in orbits just above the point of no return. Some photons might circle multiple times before escaping, others fall inward to vanish. The effect would be mesmerizing, a glowing ring of energy marking the edge between existence and silence. Crossing that edge would be uneventful. There would be no sensation, no flash, no change in the laws of physics at the exact boundary. But everything afterward would be different. The concept of outside would cease to apply. Light from beyond could no longer reach you. The rest of the universe, from that moment on, would be sealed away behind a horizon that no longer allows information to pass. You would still exist, still move, still think, but your frame of reference would now point only one way, inward. The gravity inside Ton 618 is almost unimaginably gentle compared to smaller black holes. Paradoxically, the larger the black hole, the less intense the tidal forces near its horizon. For a stellar mass black hole, the difference in gravitational pull between your head and your feet would be enough to tear you apart instantly, a process sometimes called spaghettification. But for Ton 618, with its enormous radius, those differences would be minor at first. You could cross the horizon intact, still conscious, still falling freely. The distortions would come gradually, growing as you moved deeper toward the centre. The deeper you fell, the stranger the relationship between time and space would become. The horizon behind you would close, not as a surface but as a concept. Light could still travel within your region, but it would all move inward, converging toward the same inevitable point. The geometry of space-time would guide everything, particles, light, even time itself, toward the singularity. To describe this with ordinary language is impossible, because every word assumes a perspective that no longer exists there. There is no down, no centre, no direction. There is only the progression of curvature, increasing endlessly. If you could observe your surroundings during this descent, you might see light from the outer disk still reaching you, distorted and blue-shifted by gravity. The photons that managed to follow you inward would grow more energetic, brighter, harsher, as if the universe itself were concentrating into a final burst of information. The radiation wouldn't illuminate objects because there would be nothing left to reflect it. The light would simply fill space, compressed into a storm of energy where space and time themselves begin to break down. At some point, the equations we use to describe reality would stop working. Relativity predicts infinite curvature at the singularity, a point of zero volume and infinite density. But infinity in physics usually means ignorance. It's the mathematical way of saying that our theories no longer apply. Something happens beyond that limit, but we don't know what. Perhaps matter is compressed into a form we can't yet describe. Perhaps space-time connects to another region, another universe. Perhaps the collapse halts at a quantum scale, creating something that persists beyond destruction. For now, all of that lies beyond what can be tested. The journey inward would end not with an impact, but with the breakdown of every coordinate system. Space would no longer be something that can be measured. Time would no longer flow in a way that can be experienced. There would be no before or after, no cause or effect, no observer and observed. Everything would converge into one indistinguishable state, the singular heart of Ton 618. From the outside, that convergence is hidden, its effects seen only in the gravity it exerts and the light it prevents from escaping. It's tempting to imagine what lies inside as a place, but it's better understood as a boundary in our understanding. The inside of a black hole is not a location within space. It's a region where our concept of space stops making sense. Some physicists speculate that the singularity could be replaced by a finite core of quantum gravity, where space-time itself becomes discrete, made of fundamental units rather than continuous fabric. In that view, falling into a black hole doesn't mean disappearing into nothing but entering a domain governed by new laws we have not yet discovered. There's also the question of information. According to quantum theory, information about a physical system cannot be destroyed. But if matter and light vanish beyond the event horizon, where does that information go? One hypothesis is that it remains encoded on the horizon itself, stored in two-dimensional form, a kind of hologram containing everything that ever fell in. Another idea is that information leaks out slowly through Hawking radiation, preserving the total balance of the universe. In either case, Ton 618 becomes not just a gravitational monster but a library, holding the unread data of everything it has consumed. If that's true, then falling in might not mean annihilation in the absolute sense. The details of your structure, your energy, even your history could be preserved in some abstract form on the horizon, scrambled beyond recognition but not erased. The universe, it seems, refuses to forget. It may transform and conceal, but it keeps its records. In that way, the fall into Ton 618 could be thought of not as disappearance but as translation, the conversion of physical existence into geometry and information. From the outside, none of that process would ever be seen. To an external observer, your fall would be frozen in time, your light dimming until it merged with the background glow of the accretion disk. Ton 618 would continue to feed, continue to radiate, indifferent to what happens beyond its horizon. The story of the infalling matter would remain sealed, written in a language the rest of the universe cannot read. The idea of crossing that boundary forces us to confront the nature of knowledge itself. Every observation, every theory, every equation stops at the event horizon. Beyond it, speculation begins, sometimes mathematical, sometimes philosophical. It's one of the few places in science where mystery is not just tolerated, but necessary. The horizon is a line that defines not just what can be seen, but what can be known. It's the physical embodiment of the unknown, a reminder that there are real limits to comprehension. And yet that same limit gives rise to beauty. The fact that we can predict the behaviour of matter as it approaches the horizon, the fact that we can describe the geometry of space-time with such precision, shows that even at the edge of knowledge, reason holds. The universe may contain mysteries beyond understanding, but it also follows patterns that we can trace up to that edge. TON 618's event horizon, smooth and absolute, is both a barrier and a perfect example of nature's consistency. To imagine falling in, therefore, is not an act of doom but of curiosity. It's the mental version of crossing that boundary, exploring what lies beyond the reach of observation through thought and theory. In that sense, every scientist who studies TON 618 is already falling inward, deeper into the curvature of understanding. The equations that describe black holes are not just mathematics. They're maps of that descent, guiding thought toward the singularity of knowledge where everything converges into one unified question. What happens next? The answer remains suspended, just like the image of a falling observer frozen above the horizon. It may never be seen, but it continues to exist as possibility. The journey toward TON 618, real or imagined, is the same journey science takes toward every unknown. They fall into deeper layers of reality, where certainty dissolves into wonder, and where even the most complete understanding opens only into more questions. And so, if you could fall in, perhaps that's what you discover, that the final destination is not destruction, but comprehension taken to its limit. That beyond light, beyond time, beyond form, there remains a kind of continuity, the persistence of existence in ways we can't yet describe. TON 618, silent and unreachable, stands as both a real and symbolic horizon, a place where matter, energy and knowledge all meet their boundaries, and beyond which lies the next step, still waiting to be understood. Beyond the point where light can escape, there is no brightness, no radiance, no signal. The world becomes something entirely different, not a place of colour and motion, but of geometry and inevitability. The stillness beyond light is not absence, it's a different kind of order. For TON 618, that stillness defines its true nature. Everything that happens near it, everything we see and measure, the glow of the accretion disk, the jets, the radiation, is a reaction to that stillness. It's the universe expressing what cannot otherwise be seen. When we speak of the event horizon as a boundary, it's easy to imagine a solid surface. But in truth, it's not a wall. It has no material form, no thickness, no texture. It's a mathematical limit, a point in space-time where all paths lead inward. It's where light loses its freedom, where time and space change their relationship completely. Inside that boundary, motion continues, but not in the way we understand it. Everything moves toward the same destination, and nothing ever returns. To call that stillness might seem strange, because within it, gravity reigns in its most extreme form. Yet from an external point of view, that's exactly what it becomes. Motion frozen by the stretching of time. If you could watch matter fall toward TON 618, you'd see it slow down as it approaches the horizon, its light red-shifting until it fades from sight. From your perspective, the infalling object would never cross. It would linger, suspended forever, frozen in time. That's the illusion created by gravity's distortion of space-time. From the falling object's point of view, however, there is no pause. It crosses freely, falling inward until every direction leads to the same end. Two truths coexist, equally valid within their own frames. To the universe outside, everything near the horizon becomes still. To the universe inside, everything continues. The stillness then is relative, an effect of distance and perception. But it carries meaning beyond physics. It shows that even in the most violent regions of space, there is a kind of balance. The energy released by Ton 618's accretion disk, the motion of particles spiralling at near-light speeds, all of it exists because of what the horizon represents. A perfect equilibrium between motion and rest, between visibility and concealment. It's the boundary where the universe expresses both its limits and its laws at once. Inside that horizon, the concept of light ceases to matter. Photons, the carriers of all visible information, can no longer move outward. They are trapped by curvature, their paths bending endlessly inward. Without light, there's no way for an external observer to know what happens beyond. But physics allows us to infer some properties of that region. The mathematics of general relativity describes how mass, energy, and curvature interact. From those equations, we can calculate the behaviour of space-time within the black hole's influence. The stillness beyond light, then, is not unknowable. It's unobservable, a distinction that matters deeply. Relativity tells us that space-time inside the horizon is not static. It continues to evolve, to carry matter and energy inward toward the singularity. But the flow of time reverses roles with the flow of space. The direction that once represented forward in time becomes toward the centre. In that regime, all futures converge into a single path. There are no choices, no detours, no return. Every particle, every quantum of energy, every bit of information follows that same inescapable trajectory. It's easy to imagine this as annihilation, but that isn't quite right. The laws of physics suggest that even here conservation holds. Energy cannot simply disappear. The total mass energy of the black hole increases with every particle that crosses the horizon. The stillness is not void, it's accumulation. Ton 618's immense gravity comes from this process, from everything it has gathered, everything that now exists beyond light. Each atom that fell in still contributes to its total curvature, still shapes the space-time around it. In that sense, nothing truly vanishes. It becomes part of the geometry itself. This idea changes the way we think about absence. The interior of Ton 618 is not nothingness. It's the densest concentration of something that can exist. The silence there is not emptiness but saturation, the point at which motion, energy and form reach their absolute limits. The result is not chaos but perfect order. Space and time, matter and energy, all obeying one principle with complete consistency. Nothing can escape. That principle defines not just the black hole but the boundary of understanding itself. Even from outside, that stillness exerts a profound influence. The gravity of Ton 618 shapes everything around it. The paths of stars, the orbits of gas clouds, the jets that erupt from its poles. Those jets paradoxically carry energy outward from a system that traps light. They're powered not by the interior but by the disk and the magnetic fields outside the horizon. As matter spirals inward, it twists those magnetic fields, channeling some of the energy away in the form of relativistic outflows. The black hole's rotation adds to the process, dragging space-time itself around with it. That phenomenon, known as frame dragging, creates the conditions that allow energy to escape even as matter falls in. If Ton 618 spins, its horizon would not be spherical but slightly flattened, its geometry described by the Kerr solution to Einstein's equations. The region around it, the ergosphere, would be a zone where nothing can remain still, relative to distant space. Even light must rotate along with the black hole. Within that region, it's possible, at least theoretically, to extract energy, a process known as the Penrose mechanism. It shows that even near absolute stillness, motion persists in subtle forms. The universe always leaves an opening for transformation, even in its most extreme states. The stillness beyond light, then, is not the end of physics, but its most complete expression. Every equation we know continues to work there, right up to the singularity. Only at that final point where curvature becomes infinite does our understanding fail. Until then, everything follows rules, predictable, consistent, and universal. The event horizon marks the threshold where predictability remains but visibility ends. It's the line between knowledge and faith in the consistency of nature. In some ways, the idea of the black hole interior mirrors the history of human thought. For centuries, philosophers and scientists have sought the limits of comprehension, the points beyond which reason cannot pass. In cosmology, those points are real, not metaphorical. The singularity is one such limit. It's not that we lack imagination, it's that the structure of space-time itself prohibits observation. The universe hides part of its own design, not out of secrecy, but because the laws that define it make concealment inevitable. And yet, through theory, we reach beyond that concealment. We know that inside the horizon, gravity dominates all other forces. We know that matter is compressed to extreme densities. We know that time behaves differently, that causality becomes one-directional. These conclusions are not guesses. They are consequences of equations tested in countless other contexts, from planetary orbits to the bending of light around stars. The stillness of TON 618, unseen though it is, follows from the same laws that describe falling apples and circling moons. That unity between the familiar and the incomprehensible is one of the great triumphs of physics. Some scientists speculate that the stillness beyond light may not last forever. Quantum effects at the horizon could cause black holes to lose mass slowly through Hawking radiation. If that's true, TON 618 over timescales longer than we can imagine would gradually fade. It would evaporate, particle by particle, until nothing remained but radiation, a faint whisper of what once was. The process would take vastly longer than the current age of the universe, but it suggests that even the most eternal-seeming stillness might eventually yield to change. Whether that evaporation truly occurs remains uncertain. For supermassive black holes, the effect is too weak to detect. The surrounding cosmic background radiation overwhelms any possible emission. TON 618, therefore, may persist for trillions upon trillions of years, long after stars have burned out and galaxies have gone dark. It could become one of the last luminous remnants of a dying cosmos, a silent monument to the era when the universe was full of light. Its stillness would then be not just physical but temporal, a quiet persistence in a universe that has forgotten motion. Thinking about that future stretches imagination as much as falling in does. In the deep time of the cosmos, everything changes. Stars exhaust their fuel, galaxies drift apart, and even atoms may decay. Black holes, for now, stand as the final anchors of structure. They are the keepers of mass, the last reservoirs of gravitational order. The stillness beyond light is their gift to the universe, a way of storing the past within geometry, preserving what once was in the curvature of space-time. For us, that stillness is a symbol of both limit and continuity. It reminds us that even where light cannot reach, the laws of nature remain intact. The universe doesn't stop working at the horizon. It continues, unseen but consistent. TON 618's existence proves that those laws hold across scales so vast and conditions so extreme that no human experiment could ever reproduce them. It's a validation of the idea that order persists even when perception fails. If you could somehow look back from inside, there would be nothing to see. Not because there's nothing there, but because sight itself loses meaning. The absence of light does not mean darkness. It means the absence of observation. Stillness here is not silence, but completeness. Everything that can happen has already happened. Everything that can move has already moved. And everything that can exist has become part of the geometry. There is nothing left unresolved, nothing left in motion. It's the purest form of equilibrium that the universe allows. In that way, the stillness beyond light is not a void to be feared, but a condition of balance. It's the endpoint of energy, the fulfillment of gravity's pull, the completion of every trajectory. The cosmos, vast and active, always tends toward equilibrium. Stars burn until they stabilize or collapse. Planets cool until they reach thermal balance. Even the expansion of the universe moves toward a state of uniformity. Black holes are the ultimate expression of that tendency. Regions where balance becomes total, where the outward and inward forces of nature meet and cancel in perfect stillness. And yet, that stillness still interacts. It shapes orbits, bends light, and defines structure across billions of light years. It's paradoxical, silent, invisible, but powerful beyond measure. TON 618's presence is felt far beyond what it can illuminate. It organises the galaxy around it, influences the space between stars, and affects even the path of light travelling near it. The stillness beyond light may be invisible, but its influence reaches everywhere gravity does. When we think about it this way, the boundary between light and stillness becomes not a division but a connection. The visible universe, with all its stars, galaxies and radiation, exists because of what happens beyond visibility. The hidden and the seen are two halves of the same reality, bound together by the same laws. TON 618's quiet heart and its blazing disk are not opposites. They're expressions of one system in balance. The stillness beyond light gives meaning to the motion outside, just as darkness gives meaning to light. As long as we continue to study black holes, we'll keep approaching that boundary, not physically, but intellectually. Each new observation brings us closer to understanding how the universe maintains its harmony. The stillness beyond light will remain unseen, but it will always be there, holding the shape of the cosmos together, anchoring it with the weight of everything that has ever fallen inward. And perhaps, in the quiet balance that TON 618 represents, there is a reflection of something deeper about existence itself, that even in the absence of light, even where perception ends, the universe continues to be whole. That wholeness, unseen but complete, is the stillness beyond light. Somewhere out there, TON 618 still glows. Its light, old beyond imagining, continues to move across the expanding universe, crossing the silent gulfs between galaxies. Every photon it sends carries the trace of a time when the cosmos was young and unrestrained, when creation itself was loud with energy. That light has been travelling for over 10 billion years and is still on its way, crossing distance after distance, through regions of space that may now be empty or filled with new galaxies born long after it began its journey. Some of those photons are finding us now, some will pass by unnoticed, some may never be caught by any eye or instrument at all. But they continue, indifferent to distance, bearing the quiet message of what once was. And here we are, on a small planet orbiting an ordinary star, using fragile instruments to listen to that message. It's a strange thought that the same light that left the disk of TON 618 before the Earth existed can enter our atmosphere, touch a mirror, and end its ancient voyage as a faint signal in a detector, to be turned into numbers, graphs, and understanding. That connection between something born in the depths of a black hole's gravity and the small act of observation here now is almost too vast to contain in language. Yet it's real. It's happening every moment. The universe, across its scale, is always speaking to itself through light. When you look up at the night sky, it's easy to forget how much of it is history. Every point of light is a memory. Every faint glow is an event long over. The stars are letters written long before we were here to read them. The galaxies are sentences in the same story, unfolding across billions of years. TON 618 is a paragraph written in the earliest chapters, bright, intense, and enduring. Its light reaches us as a whisper, soft enough to be drowned by the noise of our own planet, yet carrying more information than any words could hold. It's tempting to think of the universe as distant, as something separate from us. But when we listen carefully, when we trace the path of that light, the separation begins to fade. The same physical laws that govern the black hole's event horizon shape the neurons firing in our brains. The same particles that once swirled in its accretion disk drift through our blood. The atoms that make up our world were forged in stars that lived and died under the same cosmic rules. The universe is not something we look at. It's something we're part of. Every observation is the universe examining itself, every question a continuation of its own unfolding. If you were standing outside on a clear night, far from cities and their glare, and looked straight into the darkness, you wouldn't see Ton 618 with your eyes. It's too distant, too faint, its light stretched and weakened by time. But it's there, in that direction, waiting in the depths. You could look for hours and never glimpse it, but knowing it's there changes the way the darkness feels. What once seemed empty becomes full. Every patch of sky holds multitudes. Every quiet moment carries echoes of creation. There's something soothing about that idea, that the silence of space is not the absence of sound, but the accumulation of it over time. The background radiation that fills the universe, the faint hum of energy that telescopes detect, is the afterglow of everything that ever happened. It's a reminder that nothing truly disappears. Not stars, not galaxies, not even the light that leaves them. It all remains, stretched across time, fading, but not gone. The same is true for us. Our brief moments, though small on the scale of the cosmos, become part of that continuum, absorbed into the same vast persistence. When scientists study Ton 618, they often talk about its numbers. 66 billion solar masses, 10 billion light-years of distance, luminosities beyond measure. Those numbers are impressive, but they're not the whole story. Behind them is something quieter. The simple fact that we can know this at all, that human beings, confined to one small planet, can understand the physics of objects so far away that their light began before our species existed. That ability to reach outward with thought, to find coherence in what seems infinite, might be the most astonishing thing the universe has done so far. The act of understanding itself feels like an echo of cosmic creation. The same forces that formed black holes and galaxies also made minds capable of perceiving them. In that way, curiosity is not separate from the universe, but one of its natural consequences. The same laws that drive matter to collapse under gravity also drive consciousness to explore. The same gravity that draws everything inward also draws thought outward, toward discovery, toward meaning. Ton 618, unknowable as it may seem, is part of that dialogue. Its existence invites the question, and the question completes the circle. If you could sit in silence, perhaps in the deep hours of the night, and think about that, the distance would start to feel smaller. You and that distant black hole would seem less like separate entities, and more like parts of one process. Energy becoming structure, structure becoming awareness, awareness returning to energy in the act of observation. Everything connected, not by metaphors but by physics. It's the same universe, continuous from the core of Ton 618 to the quiet moment of breath you're taking now. The stillness between us and that distant light isn't empty. It's filled with time, with the slow unfolding of everything that ever was. The light from Ton 618 moves through that space, and so does the light from our own sun. The signals from our satellites, the faint traces of every radio transmission humanity has ever made. All of it travelling outward together, mixing into the same fabric. Somewhere, far in the future, a fraction of that signal might drift through another galaxy, long after we're gone, and someone, or something, might notice it, the same way we notice Ton 618 now. The exchange never ends. If you think about it long enough, the universe starts to feel less like a stage and more like a conversation. Each particle, each photon, each gravitational wave is a line of dialogue. Black holes speak in curvature, stars in radiation, planets in motion. And somewhere in that ongoing exchange, life began to listen. Every observation, every experiment, every quiet night of looking up is part of that same act of listening, one that began billions of years before there were eyes to see or minds to wonder. The night sky above us is the most ancient text we have, written not in symbols but in light. Each photon is a syllable, each spectrum a word, each galaxy a chapter. Ton 618 is one of the oldest pages in that text, preserved against the erasure of time by distance and gravity. We've only begun to learn how to read it. The more we learn, the more we realise how vast the story is and how small our role, yet how essential. Without readers, even the greatest story remains unread. Without curiosity, even the brightest light remains unseen. It's remarkable how the act of looking outward changes what we see inwardly. Knowing that black holes exist, that gravity can shape time and light so completely, alters the way we think about our own existence. It puts our lives in perspective, not to diminish them, but to expand them. The same physics that bends starlight also shapes the rhythm of every heartbeat. The same entropy that drives galaxies toward equilibrium governs the fading of a sunset. The patterns repeat, from the cosmic to the intimate, endlessly. There's comfort in that repetition. It means the universe is consistent, dependable, and whole. It means that the light from Ton 618, though distant, follows the same rules as the light in your room. It means that even at the edge of understanding, we are still within the same structure. Every observation brings the infinite closer, not because the distance changes, but because our understanding bridges it. Imagine, for a moment, that you could see the sky not just as points of light, but as it truly is. A map of time. Closer stars would shimmer with recent light, while distant galaxies would appear as faint memories, their glow softened by age. Ton 618 would be among the oldest lights visible, a remnant of the universe's youth. Looking at it would be like looking through layers of history, all compressed into one field of vision. Every direction would point to another era, another chapter of creation, another fragment of the same story. And at the centre of that field, unseen but certain, would be the awareness looking back. That awareness, yours, mine, ours, is as much a part of the universe as any star. We tend to separate ourselves from what we observe, but there's no real boundary. The atoms in our bodies are ancient, recycled countless times through stars and dust. Some may have come from quasars like Ton 618, forged in the same furnaces of gravity and light. When you think of it that way, the distance between observer and observed becomes smaller still. The light we study once flowed through matter that may now flow through us. The cycle is complete, continuous, and endless. As the universe expands, most of its light will eventually drift beyond reach. The most distant galaxies will fade from view, their photons stretched into wavelengths too long to detect. Black holes like Ton 618 will remain, slowly consuming the remnants of their surroundings, until even they cool and quiet into invisibility. The cosmos will grow dark, and the last echoes of creation will fade into background radiation. But the fact that we can see it now, here, in this brief window of cosmic time, is extraordinary. We exist during the era when the universe is visible, when the light of its beginnings still reaches us. We are witnesses to its story while it's still being told, and though that story will continue long after we're gone, our awareness of it gives it meaning in this moment. The light from Ton 618 will keep travelling, whether we watch it or not, but knowing it's there changes everything. It turns the night sky from emptiness into connection. It transforms silence into conversation. It gives weight to wonder. So, here we are, you, me, and the infinite night. The same night that has covered every world since the beginning, the same darkness filled with ancient light. Somewhere out there, Ton 618 still shines, unseen but not forgotten, its photons still crossing the distance toward whoever might come after us. And somewhere here, In this small corner of the same universe, we keep looking up, still listening, still learning, still part of the same unfolding story. There's no need to end that story because it never really ends. The light keeps travelling, the questions keep forming, the stillness beyond light keeps holding everything together, and the act of wondering, quiet, steady, endless, keeps it all alive.